Hello, my friends. Welcome, and thank you for joining me tonight. Whether you're unwinding after a long day or drifting into a peaceful rest, I'm so glad you're here. Tonight, we're going to explore something truly mysterious: dark matter. Imagine this, something in the universe that you can't see, touch, or even measure, yet it's all around us. A force so powerful it influences everything, but it remains hidden, invisible. This is dark matter, a force we can't fully explain, yet we know it's out there. Quiet, invisible, yet so real. Intrigued? Let's quietly explore this mystery together. Before we begin, tell me where you're watching from in the comments below. I love feeling connected with all of you, even from far away. And if you're ready to relax and hear some fascinating cosmic stories, make sure to like and subscribe, but only if you genuinely enjoy the content. Now, let's start this journey. Take a deep breath and let's begin. Stars and galaxies move in ways that don't quite make sense. When we only consider the things we can see, something invisible must be there, holding everything in place, helping to keep the universe balanced. Scientists believe that dark matter makes up about 27% of the universe. The matter that we can see, the stars, planets, and even ourselves, only accounts for 5%. The rest is filled with something called dark energy, which plays a different role altogether. Dark matter surrounds galaxies like a halo, silently holding the very structure of the universe together. The idea of something invisible shaping the cosmos began in the 1930s when a scientist named Fritz Zwicky noticed something strange. He found that galaxies were moving too quickly for the amount of mass they seemed to have. Many years later, another scientist, Vera Rubin, looked at how stars in spiral galaxies were moving. She noticed that stars on the outer edges were moving just as fast as those in the center. This was a mystery until they realized that there must be invisible mass, dark matter, helping to keep everything in balance. Scientists have been searching for answers about what dark matter is ever since. One possibility is that dark matter is made up of particles that are very difficult to detect. One type of particle scientists have studied are called WIMPs. These particles are heavy but don't interact much with regular matter. Another idea is that dark matter could be made of even lighter particles called axions, which are even harder to find. While scientists haven't yet directly seen dark matter, they are looking for it in all sorts of experiments. Some of these experiments are deep underground, in labs that are shielded from all outside light. These labs use very sensitive instruments, hoping for a rare signal that might prove dark matter exists. Though no direct proof has been found yet, every experiment helps scientists learn a little more, and each discovery narrows down what dark matter could be. The search continues, quietly and patiently. Scientists are also looking for indirect evidence. For example, the Fermilab telescope looks for gamma rays, special kinds of light, that might be emitted by dark matter interacting with other particles. These gamma rays could be coming from places with a lot of dark matter. Sometimes scientists find signals that look interesting, but none of them have been strong enough to be certain. By studying galaxies and smaller galaxy groups, scientists are learning more about how dark matter behaves. These studies help test different ideas and theories about dark matter. Some scientists still wonder if dark matter even exists, suggesting that maybe gravity works differently on a much larger scale. But so far, the idea of dark matter still fits the best with what we see in the universe. The most accepted model of the universe is based on something called lambda CDM. This model helps us understand how galaxies and clusters of galaxies form and how they are arranged. It shows how dark matter creates filaments, or strands, connecting different galaxies. Without dark matter, these simulations wouldn't work. So it seems like dark matter plays an essential role in the creation of the universe. Without it, the universe wouldn't have come together the way it did. Dark matter also played a part in the creation of the very first galaxies. In the beginning of the universe, it helped create areas where gravity was stronger. These regions pulled ordinary matter in, causing the first stars to form and the first galaxies to take shape. In this way, dark matter helped the universe grow quickly. Without it, things might have happened much more slowly. Some events, like galaxy collisions, also give us clues about dark matter. In the case of the bullet cluster, scientists observed that visible matter and gravity seemed to be separated. This told them that dark matter must still be there, influencing gravity, even as visible matter moved away. These observations are like nature's way of giving us hints, showing us how dark matter works. In the field of particle physics, scientists continue to explore how dark matter fits into the bigger picture. Some ideas suggest that dark matter could be part of a larger theory, like supersymmetry or extra dimensions. Scientists at places like the Large Hadron Collider are searching for new particles that could explain dark matter. Although they haven't found anything yet, each new experiment helps narrow down where to look next. Dark matter is still one of the greatest mysteries of science. We know it's there because we can see its effects, but we're not sure what it's made of. Every new experiment brings us a little closer to understanding it. The search continues, helping us to understand the universe just a little bit more with every discovery. The habitable zone of a star is an area where life could possibly exist. It's the place where the temperature is just right for liquid water to be found on a planet's surface. In our solar system, Earth is in this zone, as is a small part of Mars. This zone depends on how far a planet is from its star and how much light that star gives off. What's interesting is that the habitable zone isn't fixed. As a star gets older, it changes. The Sun, for example, has become brighter over time, and because of this, the habitable zone has slowly moved outward. Earth, in fact, is slowly drifting toward the inner edge of this zone. Scientists predict that in about 1 or 2 billion years, Earth might no longer be in the habitable zone. The Sun will continue to shine more brightly, and this will gradually make Earth's surface too hot to support life. Mars, on the other hand, is near the outer edge of the habitable zone. Right now, it's not able to support liquid water because its atmosphere is too thin. However, as the Sun grows brighter, Mars might find itself in a more stable position to sustain water on its surface. In a very distant future, Mars might even have the necessary conditions for life. If we look back in time, Venus may have once been on the edge of the habitable zone. It's possible that it was once warm enough for liquid water. However, Venus experienced a runaway greenhouse effect which made it too hot to sustain life. Mars, on the other hand, might have had more favourable conditions for liquid water in the past, which is suggested by the discovery of old riverbeds on its surface. Beyond our solar system, there are other places where the habitable zone might look different. The TRAPPIST-1 system, for example, has planets that orbit very close to their star because it is much cooler than our Sun. Even though these planets are very close, they might still have the right conditions for life depending on their atmospheres. Other stars, like red dwarfs, have very long lifespans, so their habitable zones shift very slowly. This allows planets to stay in the habitable zone for much longer periods, which could give life time to develop. But these stars also have bursts of energy that might make it harder for planets to keep their atmospheres intact. Still, stars like this are good candidates for finding life. The planet Kepler-186f orbits in the habitable zone of a smaller star. It's very similar to Earth in size, and its position allows it to receive the right amount of energy to potentially support liquid water. However, being in the habitable zone doesn't guarantee that a planet can support life. Other factors, like atmosphere and climate, also play a big part. As we study the habitable zone, we also look at places beyond the classic zone, like moons in our solar system. Moons like Europa and Enceladus have liquid oceans beneath their icy surfaces, kept warm by heat from inside their planets. This shows us that there are other ways a planet or moon can support life, even outside the traditional habitable zone. In the end, the concept of the habitable zone is not just about location. It's about a balance of many factors, from the type of star to the atmosphere of the planet, that all work together to create the conditions needed for life to grow and flourish. The universe is full of wonder, and there are so many mysteries still waiting to be discovered. One of the most fascinating things to study is how the habitable zone, the space where life can exist, changes over time. This zone, like the gentle ebb and flow of the tides, shifts through the ages. By observing our own solar system and others, like the TRAPPIST-1 system and Kepler-186f, scientists begin to understand how life might arise and persist. The space for life in the universe moves with time, like a quiet dance that's happening all around us. As we look deeper into space, we realize that galaxies too are not still, frozen worlds. They interact with one another over eons, moving slowly but surely. One of the most dramatic of these interactions is when galaxies collide, which sounds frightening, but it's a slow, natural process. It's like two dancers gently joining together, their movements guided by gravity. When two galaxies meet, they often merge, with the larger one gently drawing in the smaller one. This process, called galactic cannibalism, is not as rare as we might think. In fact, our own Milky Way has already absorbed several smaller galaxies during its long journey through space. For example, the Milky Way is currently in the process of swallowing the Sagittarius dwarf galaxy. This peaceful, slow process will take billions of years, gently reshaping the stars, gas, and invisible dark matter that flow between the two galaxies. Although these collisions might sound violent, they rarely result in the stars themselves crashing into one another. Stars are spaced far apart, even in the densest parts of a galaxy, but the gas that fills these galaxies does collide and compress. This compression triggers the birth of new stars, as if the galaxies are quietly giving birth to new life in the midst of their cosmic dance. One of the most studied galactic collisions is that of the antenna galaxies, located around 45 million light-years away. These two galaxies are stretching out long arms of stars and gas as they merge, and through the power of space telescopes, we can see the bright new stars being formed in these arms. It's like watching the sky paint itself with light, a slow magical process that has been unfolding for millions of years. But the most exciting part is yet to come. In about 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy, the largest in our local group of galaxies. This will result in a new galaxy, one shaped by the merging of the two. It will be a slow, graceful process, like two great rivers joining to create a new path. During this cosmic event, our solar system may be gently moved to a new place in the sky, but it will continue to travel through space, as it always has. As these galaxies merge, the supermassive black holes at their centers will also draw closer to one another. Eventually, they will merge as well, sending out ripples in the fabric of space known as gravitational waves. These waves will carry tremendous energy across the cosmos. Telescopes like LIGO and LISA are listening carefully for these gentle cosmic whispers, trying to understand the deep mysteries of the universe. Galactic cannibalism is part of the larger story of how galaxies grow and evolve. It's like a tree that slowly grows and stretches its branches over time, reaching out to connect with others. When smaller galaxies collide, they add their stars, gas, and dust to the larger galaxy, building something even more magnificent. This process has shaped the universe for billions of years, and it continues silently and slowly in the background of our existence. By watching these galaxies, scientists can learn about the history of the universe, seeing how it has changed and how it will continue to change. In addition to these large collisions, galaxies also interact with smaller satellite galaxies that orbit them. These small galaxies circle around larger ones, like moons around planets. The interactions between them can cause subtle changes, like gentle ripples in a pond. These interactions might cause stars to shift in their orbits or gas to flow in new directions, adding new life and energy to the larger galaxy. Even in these smaller, quieter interactions, we can see how galaxies grow and evolve. Each collision, whether small or large, leaves its mark. Galaxies change shape and form, and they begin to look different as they merge. Some may lose their spiral shape, becoming smooth elliptical galaxies instead. The effects of these collisions are not always the same. They depend on how the galaxies collide, their size, and the amount of gas available. It's like the difference between a gentle breeze and a strong wind. Each collision brings its own unique story. One of the most mysterious phenomena in the universe is the fast radio burst, or FRB. These are quick bursts of energy, lasting only a few milliseconds, but they carry an enormous amount of power. They come from distant galaxies, billions of light-years away, and are as surprising as a flash of lightning on a calm night. Although these bursts were first discovered only in 2007, hundreds of them have been catalogued since then. But their origin is still unknown, adding to the sense of mystery that surrounds them. Some FRBs appear only once, like a shooting star that flashes brightly and then disappears, Others, however, repeat, coming from the same spot in space, over and over again. This repeating pattern makes scientists think there may be something special about these bursts, but the exact cause is still a puzzle. Many researchers believe that FRBs might be connected to neutron stars, magnetars, or black holes. These are cosmic objects that are known for releasing huge amounts of energy, like giant hidden furnaces in the sky. In 2020, an FRB was linked to a magnetar in our own Milky Way, which gave scientists more clues about their source. But the bursts that come from other galaxies are much more powerful, suggesting that there could be other factors at play. No single explanation has yet explained all of the FRBs, but the search continues. Another curious mystery comes from a star known as Tabby's star. In 2015, scientists noticed that this star's brightness fluctuated in strange patterns, unlike anything seen before. The variations didn't match the usual explanations, like planets passing in front of the star or spots on the star's surface. At first, people wondered if this could be the result of artificial structures, perhaps signs of an alien civilization. But the most likely explanation today is that clouds of dust caught in irregular orbits are passing by the star, causing its light to change. Stars are also known to send out regular pulses of energy, which are called pulsars. These stars send out beams of radiation, and sometimes their pulses don't behave in the way scientists expect. This adds to the mystery of the universe as we try to understand how these extreme objects work. Each of these signals, whether it's a fast radio burst or the unusual behavior of a star, reminds us of how much there is still to learn about the universe. The signals may come from distant stars, galaxies, or mysterious cosmic objects, but they all point to the same truth. The universe is full of surprises. Every discovery opens a door to a new world, a world that we can only begin to imagine. By studying these signals, scientists are learning more about the deep, hidden parts of space. Some of these discoveries come quickly, while others take years of careful observation. But with each new piece of information, we come closer to understanding the universe in all its wonder and mystery. And as we drift off to sleep, just remember, the universe, with all of its beauty and wonder, is always there, quietly unfolding in the background of our existence. It's waiting for us to discover more, slowly and gently, as we move through the vast, peaceful expanse of space. The study of the universe continues to unfold, and with it, the discovery of strange and wonderful phenomena. One of these intriguing discoveries is the fast radio burst, or FRB. These sudden bursts of radio waves lasting only a few milliseconds carry more energy than we can imagine. Even though they are brief, they can be detected from galaxies far, far away. While we don't yet know their exact origin, they are important because they can help us understand the universe better. They travel across vast stretches of space, and as they move, they scatter and change, offering clues about the space between galaxies. In this way, these mysterious signals are not just fascinating to study, but they also help us map the universe, providing valuable data that we would otherwise miss. As more of these signals are discovered, they become more varied, which suggests there isn't a single answer to explain them. Each new signal could belong to a different class of phenomena, something we haven't fully understood yet. Radio astronomy and high-energy astrophysics are fields that are constantly growing, with new discoveries made every year. We expect that with the development of more sensitive instruments, even more signals will be discovered in the coming years, helping us uncover more secrets of the cosmos. Then there's dark energy, a mysterious force that is causing the universe to expand faster and faster. This discovery, which began in the 1990s, came from studying supernovae, distant stars that explode and shine brightly for a brief time. These supernovae, known as Type Ia supernovae, act like beacons, helping scientists measure distances across the universe. What was expected to be a slowdown in the expansion due to gravity, instead turned out to be the opposite. The universe is expanding with more force than ever before, and this acceleration is driven by something we cannot see or touch: dark energy. Dark energy is thought to make up about 68% of the universe. We cannot directly detect it, but we can measure its effects by looking at the redshift of galaxies and how matter is spread out across space. This energy doesn't interact with light in a way we can observe, but the effects are clear. The data we have would not make sense without the influence of dark energy. One way scientists describe dark energy is through a concept called the cosmological constant, first introduced by Einstein back in 1917. Though Einstein himself rejected the idea, it has since been embraced as a simple explanation for the accelerated expansion of the universe. This constant represents a kind of energy that fills all of space, pushing everything apart. Another theory suggests that dark energy could be a dynamic field, one that changes over time and space. This idea, known as quintessence, imagines a force that behaves differently throughout the history of the universe. To understand these possibilities, scientists look closely at the cosmic microwave background, the afterglow of the Big Bang, and study how galaxies cluster together and how light bends as it travels through space. Most of the data we have still supports the idea of the cosmological constant, but scientists continue to explore new ideas. Instruments like the Planck Space Telescope have provided us with incredibly detailed maps of the universe, showing how energy is spread across space. These measurements reveal more about dark energy's influence, and by comparing this data with models of the universe, scientists can get a clearer picture of how this mysterious force shapes the cosmos. There's also the question of the universe's fate. If dark energy remains constant, the universe will continue to expand forever, growing colder and more stretched out. On the other hand, if dark energy changes over time, we might see events like the Big Rip, a scenario where the universe expands so quickly that it tears apart everything in it, even galaxies and stars. These are just theories based on current data, and they help us imagine different ways the universe might evolve. As we seek to understand dark energy, new missions are in development. Projects like the UK-led Euclid mission and NASA's Roman Space Telescope are designed to observe the universe with even greater precision, helping us to measure the rate of cosmic acceleration and to refine our models of dark energy. These missions hold the promise of revealing more about this elusive force in the coming decades. Dark energy remains one of the biggest challenges in cosmology. Some theories suggest it may be related to quantum vacuum physics, but current calculations suggest that the energy we expect to see is much larger than what we observe. This difference, known as the vacuum energy problem, means that our understanding of dark energy still needs work. Resolving this will require a fresh approach to our understanding of physics, and it sits at the crossroads of cosmology and quantum field theory. To explore dark energy further, scientists are also looking at structures like galaxy clusters. These massive groups of galaxies are like great cosmic laboratories, where gravity and dark energy work together. By studying how these clusters form and grow, astronomers can learn more about how dark energy affects the universe. This data, combined with other observations, helps refine our models of how the universe is shaped. In summary, dark energy is detected through its effects on the expansion of the universe and the formation of large structures. We don't know exactly what it is yet, but its influence is undeniable. As we continue to study it through new instruments and theories, we are slowly piecing together the puzzle of the universe's deepest mysteries. Discovering the true nature of dark energy may require us to rethink the fundamental laws of physics, but for now, it remains one of the most exciting challenges in modern science. And then there's the question of sound in space. In the vast emptiness of space, there is no air, no water, no medium to carry sound waves. So technically, sound cannot travel through space. But inside stars, where the conditions are dense and pressure is high, there are waves that move through the star in ways similar to sound. These waves, though not audible to our ears, can be studied by scientists. They use a technique called astroseismology to understand the inner workings of stars. Just like earthquakes reveal the inner structure of our planet, the vibrations of stars give us a glimpse into their layers and compositions. The Sun, our closest star, is the most studied example. By observing how the Sun vibrates, scientists can learn about its rotation, the depth of its convective zone, and the behavior of its core. These vibrations are subtle, but they reveal a wealth of information. Through Doppler spectroscopy, scientists measure the velocity of the Sun's surface, helping them understand how energy flows inside the star. Space telescopes like Kepler and TESS observe the vibrations of thousands of stars at once, capturing these oscillations in real time. Each star has its own unique pattern of vibrations, which allows scientists to estimate its age, mass, and size. By studying these oscillations, we gain insights into how stars live, evolve, and eventually die. Some stars, especially older ones, display different types of vibrations. For example, gravity waves, which dominate in older stars, help us understand how these stars transition from one stage to another. Mix modes, which combine pressure and gravity waves, provide even more clues about a star's inner structure. Through detailed analysis of the light coming from stars, scientists can test hypotheses about nuclear fusion, energy transport, and stellar evolution. Astroseismology is also applied to planets outside our solar system, known as exoplanets. By studying the vibrations of the star that a planet orbits, we can estimate the planet's size and mass, which helps us understand what kind of planet it might be. This method also allows us to distinguish between rocky planets, which might support life, and gas giants. In a sense, astroseismology is helping us understand the conditions for life beyond Earth. And when these star vibrations are transformed into sound, we can listen to the universe in a completely different way. The process is known as sonification, where the light variations of a star are converted into sound that we can hear. It's not actual sound in space, but it allows us to experience the vibrations in a more intuitive way. Each star has its own unique tune, depending on its internal structure. It's like each star has its own song, and through sonification we can hear its story. As we continue to study the stars, planets, and mysterious forces like dark energy, the universe slowly reveals its secrets. With each discovery, we take another step toward understanding the vast, beautiful cosmos we call home. In the quiet depths of space, there are strange and beautiful phenomena, each one unfolding a little more of the mystery of the universe. One of these wonders involves the study of how dense celestial bodies, like stars and black holes, influence the universe around them. These bodies create incredibly strong gravitational fields, which bend and shape the way waves of light and energy travel through space. This process helps scientists understand the inner workings of stars and other compact objects in the universe. By studying the faint ripples in space, like those observed in X-ray bursts, scientists can learn about the deep inner layers of stars. These ripples give us clues about how matter behaves under extreme pressure, helping us understand the hidden compositions of distant stars. This area of study, known as astroseismology, is helping us unlock the secrets of stars, allowing us to trace their life cycles and their role in the grand, peaceful flow of the universe. As we move forward, new space missions are being planned to improve our ability to observe these celestial vibrations. Projects like the Plato mission, developed by the European Space Agency, ESA, are designed to study millions of stars over long periods of time. By observing how stars change and vibrate, scientists will be able to map their inner structures, even those similar to our own sun. These observations will give us a deeper understanding of how stars evolve and how they shape the galaxy around them. Astroseismology not only helps us understand individual stars, but also connects to the larger story of the universe. By measuring the age and composition of different groups of stars, scientists can piece together the history of our Milky Way. This allows us to trace the path of stars as they move, evolve, and interact with one another, helping us understand how galaxies grow and change over time. One of the most intriguing questions in the universe is why there seems to be more matter than antimatter. According to the Big Bang theory, in the very early moments of the universe, matter and antimatter were created in equal amounts. Each particle of matter had a matching particle of antimatter, ready to cancel each other out. When matter and antimatter meet, they annihilate each other, releasing energy in the process. So logically, we would expect the universe to be filled with nothing but energy, with no stars or galaxies. But that's not what we see. Instead, the universe is filled with matter, and antimatter is incredibly rare. This imbalance is one of the greatest mysteries of modern science. Something in the early universe must have favoured matter over antimatter, and this subtle difference is known as baryogenesis. This process led to the creation of more matter than antimatter, allowing the universe to form as we know it today. Scientists are still searching for answers to explain this mystery, and new experiments are being designed to uncover the cause. One possibility is that certain particles, like neutrinos, may hold the key to understanding this imbalance. If these particles can behave as their own antiparticles, it might explain how matter came to dominate the universe. There are also other theories that propose new particles and interactions could explain this asymmetry. These ideas are being tested through cosmic simulations, which recreate the conditions of the early universe to see if they match what we observe in the present day. Meanwhile, experiments on Earth, like those at CERN, continue to search for signs of antimatter, even in the farthest reaches of space. Space telescopes like Fermilab and Integral look for radiation that could be produced when matter and antimatter collide. So far, no evidence has been found of antimatter-rich regions in space, which suggests that matter has been the dominant force since the universe's very beginnings. Even though we don't fully understand the origin of this imbalance, it is clear that it is essential to the structure of the universe. It is this small difference between matter and antimatter that allowed galaxies, stars, planets, and even life to form. Understanding why this happened is still one of the great challenges of modern physics. As we continue our exploration of the cosmos, we also learn about the nature of time itself. Time, as we know it, doesn't flow the same everywhere in the universe. According to Einstein's theory of general relativity, time moves more slowly in stronger gravitational fields. This means that time passes differently on different planets, depending on their size and the strength of their gravity. For example, on Jupiter, which is much larger than Earth, time passes just a little slower. The difference is tiny but measurable. The more massive an object, like a neutron star or a black hole, the stronger its gravity, and the more pronounced the effect on time. Close to a black hole, time can slow down dramatically. In fact, in a famous example from science fiction, the movie Interstellar shows a planet near a black hole where time moves much more slowly than on Earth. While that's an exaggerated example, it's scientifically plausible. A planet close to a supermassive black hole would experience hours while years pass outside it. This concept of time dilation isn't just about gravity. The theory of special relativity shows that time also moves more slowly for objects that are moving very fast. Spacecraft travelling close to the speed of light would experience time at a different rate than people on Earth. However, at our current speeds, this effect is tiny, though it may become significant in future space travel. Time dilation is something we also have to consider when we explore new planets. In fact, GPS satellites already account for these differences in time when they send signals to Earth. They have to adjust for the fact that time passes slightly faster in orbit than on the ground. For long-duration missions or future colonization of other planets, time dilation will play an important role in ensuring that everything runs smoothly. Even small changes in time can affect how we synchronize signals, navigate and coordinate events across space. We also use time dilation to study powerful objects like black holes. By observing how light shifts as it travels toward or away from these objects, scientists can measure how much time is being stretched in these extreme environments. This helps test the predictions of general relativity under conditions we can't replicate on Earth. The study of time is more than just an abstract idea. It is a crucial part of how we understand the universe and how we'll navigate the stars. In the future, as we travel farther into space, these subtle differences in time will guide our explorations. Time will be a constant companion as we journey across the cosmos, moving at its own pace, slowing down or speeding up as we approach different celestial bodies. In the gentle expanse of the universe, there are many mysterious and profound concepts that shape the very fabric of existence. One of these is the way time behaves, especially when it comes to the vast distances between planets, stars, and black holes. Time, as we know, is not a simple, unchanging thing. It bends and stretches depending on where you are in the cosmos and how fast you're moving. This idea, known as time dilation, is a captivating part of the universe's story. It's a reminder that time is a fluid, malleable dimension, not a fixed rule. The study of time dilation has become a key area of research, especially as space missions grow more intricate and distant. Understanding how time varies depending on where we are and how fast we travel is essential for everything, from the satellites orbiting Earth to the interplanetary probes journeying into the depths of space. Time is not the same for everyone in the universe. It slows down in stronger gravitational fields, like those near massive planets or black holes. This delicate dance of time, moving slowly or quickly depending on where you are, is one of the beautiful mysteries of the cosmos. Another fascinating topic that continues to captivate scientists is Schrödinger's cat, a thought experiment that delves into the strange, wondrous world of quantum mechanics. Imagine a cat in a sealed box, with a mechanism that depends on the decay of a radioactive atom. If the atom decays, the cat dies. If it doesn't, the cat remains alive. According to quantum theory, until the box is opened and the cat is observed, the cat is both alive and dead at the same time. This paradox highlights the peculiar nature of quantum mechanics, where things can exist in multiple states until we observe them. Though this may seem like a philosophical riddle, the underlying principles are tested every day in laboratories. Experiments have shown that tiny subatomic particles can exist in multiple states at once, a phenomenon known as superposition. In the controlled environments of labs, scientists have extended these ideas to larger systems like superconducting circuits or molecules. But the challenge remains: how do we apply these ideas to larger, more complex objects? Space, with its quiet and isolation from outside influences, offers a unique place to explore these questions. On Earth, it's hard to maintain quantum states because particles are constantly interacting with their environment. But in the vacuum of space, where the air is still and the light is dim, those quantum states can last longer. This opens up new possibilities for studying quantum behavior in space. There are even plans for future missions like the EMAC-RO project, which will test quantum superposition using particles that are 1,000 times heavier than those studied in current experiments. These studies could reveal where quantum states start to shift into what we know as classical behavior, giving us deeper insight into the nature of the universe itself. Space is also helping scientists understand another quantum phenomenon: entanglement. When two particles are entangled, they behave in a coordinated way, even if they're far apart. A satellite called Mikias, launched by China, successfully demonstrated quantum key distribution and entanglement over thousands of kilometers, showing that quantum rules apply beyond Earth's atmosphere. This opens up new possibilities for secure communication and perhaps for understanding the mysteries of the quantum world. Just as Schrödinger's cat serves as a metaphor, it now represents a frontier of science where quantum theory, cosmology, and experimental physics come together. The experiments in space, whether testing quantum superposition or entanglement, bring us closer to understanding how these strange quantum behaviors stretch and bend when applied to the vastness of space. These experiments may help us understand whether quantum behavior is flexible, or if there's a boundary between the quantum and classical worlds. In addition to these incredible studies, scientists are also exploring black holes and their mysterious behavior. For a long time, black holes were thought to be eternal objects that trapped everything, even light. However, in 1974, physicist Stephen Hawking proposed a groundbreaking idea. Black holes might not be completely black after all. According to his theory, black holes should emit radiation, which gradually leads to the loss of mass over time. This process is called Hawking radiation, and it occurs because of quantum effects near the black hole's event horizon. Normally, pairs of particles are created near the event horizon, and they quickly annihilate each other. But near a black hole, one particle can fall in while the other escapes, becoming real radiation. This radiation slowly reduces the black hole's mass, and over incredibly long periods, it could cause the black hole to evaporate entirely. The rate at which a black hole evaporates depends on its size. Large black holes, like those at the centers of galaxies, emit radiation so slowly that their evaporation would take far longer than the current age of the universe. On the other hand, smaller black holes, possibly formed in the early universe, would evaporate much faster. These primordial black holes might already be gone, or nearing the end of their lives. Although no Hawking radiation has been directly observed, the idea is supported by strong theoretical models that bring together quantum mechanics and general relativity. Many scientists believe that Hawking radiation is a robust prediction of how black holes behave, even though experimental confirmation remains a distant goal. This theory has sparked deep questions about the nature of black holes and the fundamental laws of physics, particularly when it comes to information and its potential loss. The black hole information paradox, which asks what happens to the information that falls into a black hole, is one of the great unsolved problems in modern physics. Some theories suggest that information might be encoded in Hawking radiation, while others propose new physics is needed to resolve the paradox. As scientists continue to explore these ideas, they are looking for signs of Hawking radiation in space. Space telescopes like Fermilab and upcoming missions are scanning the sky for sudden bursts of gamma-ray radiation that might be linked to black hole evaporation. Even a single confirmed detection of this radiation would be a breakthrough, not only confirming Hawking's theory, but also providing a glimpse into the deep mysteries of quantum gravity. In addition to observing the behavior of black holes, scientists are using space to learn more about time itself. Time is a strange thing, it doesn't flow the same everywhere. According to Einstein's theory of general relativity, time moves more slowly in stronger gravitational fields. This means that time passes more slowly on planets with stronger gravity, such as Jupiter, compared to Earth. This effect is very small but measurable, and it becomes much more pronounced near massive objects like black holes. Time is also affected by speed. According to special relativity, fast-moving objects experience time more slowly. This effect, known as time dilation, becomes significant at speeds close to the speed of light. Space missions must account for these differences in time when navigating the vast distances of space. Even tiny changes in time can have a big impact on mission planning, so understanding how time works in different parts of space is crucial. As space exploration continues, understanding these subtle differences in time will help guide missions and improve our ability to measure and synchronize signals across the universe. Whether it's the slow passage of time near a black hole or the tiny variations caused by the speed of a spacecraft, these delicate changes in time remind us of how connected everything is in the cosmos. With each new discovery, we come closer to understanding the true nature of time, space, and the universe itself. As we gaze at the night sky so full of wonder, there's still so much we do not understand about the universe. One of the most incredible mysteries is the idea of quantum gravity, a concept in physics that holds the potential to reshape our understanding of the cosmos. Imagine a world where we can connect the smallest particles to the grandest forces in the universe. This is what scientists hope to achieve, to unify the forces of the universe and understand everything from the tiniest atoms to the vastness of space itself. It's a goal that brings us closer to understanding the heart of black holes, those mysterious objects that appear to swallow everything around them. But what if we were to learn that black holes aren't forever? What if they could vanish, fade away into nothing? This idea, while still a theory, is growing more accepted in the scientific community. Future research and missions may soon help us witness the final moments of a black hole, and when that happens, it will be a pivotal moment in our quest to understand the universe. Radio waves from the depths of space. In 2007, a strange phenomenon began to capture the attention of astronomers. A brief burst of radio waves lasting just milliseconds appeared out of nowhere, carrying more energy than the sun could emit in several days. It was an unexpected event, one that sparked curiosity and wonder. This event became known as a fast radio burst, FRB, a fleeting yet powerful signal from deep space. FRBs are mysterious and intriguing. They appear suddenly, as if they are messages from the farthest reaches of the universe. They don't last long, and they vanish as quickly as they arrive. Telescopes across the world are constantly on the lookout for these bursts, scanning the sky for any sign of them. They often come from galaxies far, far away, sometimes billions of light years from us. While some FRBs repeat from the same location, others only occur once, adding to the enigma of their nature. Scientists believe that these bursts may come from neutron stars, which are dense remnants of massive stars. One theory is that magnetars a type of neutron star with an incredibly powerful magnetic field might be the source. If the magnetic field shifts, it could release a burst of energy, including radio waves. In 2020, this theory was strengthened when an FRB was linked to a magnetar within our very own galaxy. Still, not all FRBs fit neatly into this idea. Some repeat at regular intervals, while others seem to follow no pattern at all. Could these bursts come from binary systems where two stars, perhaps one a magnetar, orbit each other? The answers remain elusive, and scientists are working hard to unlock the mystery. There are even more unusual ideas, such as the possibility of collisions between neutron stars and black holes, or even cosmic strings, theoretical defects in space-time itself. The study of FRBs has become a new way to map the universe. When the radio waves travel through space, they interact with the free electrons scattered between galaxies, creating a unique fingerprint that scientists can study. This helps them understand not only the origins of the bursts, but also the space between galaxies. With advancements in technology, scientists are now using new arrays of telescopes, such as KIME in Canada and OSCOP in Australia, to locate the exact source of these bursts. They use slight differences in the arrival time of radio waves to pinpoint the exact location of the burst. This has allowed them to identify specific galaxies, and sometimes even regions within them, where FRBs come from. As new instruments are developed, including the Square Kilometre Array and other future telescopes, our ability to detect weaker and more distant bursts will improve. This could even reveal new kinds of FRBs, some from our own galaxy, and others that have travelled across the vast distances of time and space. Some of these bursts could even trace back to the very early universe, helping us learn about its birth. But the discoveries don't end there. FRBs could also help us understand the expansion of the universe. As radio waves travel through space, they get scattered by free electrons. This scattering, called dispersion, can be used as a cosmic ruler to measure the distance between objects in space. By comparing how much dispersion occurs with the known distance of an FRB, scientists can map the distribution of matter in the universe. This could even help us understand the mystery of dark matter, that invisible substance that makes up most of the universe's mass. As scientists continue to study FRBs, they're using advanced technologies like machine learning to help process the massive amounts of data these events generate. The bursts may appear suddenly, but they bring with them a wealth of information that can only be unlocked through careful and detailed analysis. While some stars end their lives in dramatic explosions, others take a quieter path. Some stars seem to vanish without any warning, disappearing without the usual burst of light that comes with a supernova. This silent collapse challenges our current understanding of how stars die. One such case was observed in the galaxy NGC 6946, where a massive star was monitored over several years. It showed signs of instability, but one day it simply vanished. No supernova explosion occurred, just a faint disappearance. The leading theory is that the star collapsed directly into a black hole, skipping the explosive supernova stage altogether. This idea has been dubbed the failed supernova theory. In a failed supernova, the core of the star collapses inward under its own gravity, but the outer layers fall too quickly for the shockwave to escape. Without the explosion, no bright supernova is visible. Instead, the core forms a black hole, silently swallowing the star from within. Detecting these failed supernovas is difficult because they don't shine brightly. However, astronomers are using long-term monitoring to track massive stars, looking for signs of these silent collapses. Tools like the Hubble Space Telescope and the Spitzer Space Telescope are particularly useful, as they can sometimes detect faint infrared signals that hint at the formation of a black hole. Some researchers believe that we might even be able to detect gravitational waves from these events. If the collapse of a star produces ripples in space-time, we might be able to measure them with detectors like LIGO, though the current technology is not yet sensitive enough to catch these signals unless they occur relatively nearby. The implications of failed supernovas are far-reaching. If many stars collapse without exploding, the number of stellar black holes in the universe might be larger than previously thought. This would also affect our understanding of how galaxies evolve and how chemical elements are spread throughout the cosmos. Stars that explode release heavy elements into space, But a failed supernova would not scatter these materials, leaving the universe with fewer new elements. The mystery of how stars die and the nature of cosmic bursts like FRBs is still unfolding. As our tools and technology improve, the puzzle pieces are slowly coming together. Every discovery, every new piece of data brings us a little closer to understanding the vast and complex universe we live in. The universe is full of wonders, both large and small. With each new observation, we gain insight into the forces that shape our world and beyond. Whether it's the mysterious signals from far-off galaxies or the silent collapses of stars, we are continuously learning more about the hidden depths of space. And as we continue to explore, we will always be on the lookout for the next great mystery to unravel. In the quiet of the night, as we drift off to sleep, we can rest easy knowing that the universe still holds many secrets waiting to be discovered, gently guiding us toward a peaceful tomorrow. Advanced telescopes like the Vera C. Rubin Observatory may soon be able to detect these quiet, low-light events in the sky. Finding them will give us important proof of how stars can end their lives in different ways. As more stars are studied and observed, scientists believe we will uncover more of these missing giants, the stars that quietly fade away. When a bright star disappears without any dramatic explosion or debris, it gives us an important clue about what's happening. By combining different types of data like light, infrared, neutrinos, and gravitational waves, we can improve how we detect these mysterious events. This approach, known as multi-messenger astronomy, is key to studying these quiet star deaths. Stars that vanish without leaving any trace challenge what we once believed about how stars die. Normally, when stars end their lives, they explode in a huge burst of light, a supernova. But some stars might end their lives quietly, disappearing into the darkness without a sound. This gentle collapse is just as powerful and just as important in shaping the universe. It's a beautiful reminder of how physics, black hole formation, and astronomy all come together to help us understand the cosmos. One fascinating idea that comes up in this journey is the concept of white holes. White holes are purely theoretical, imagined as the opposite of black holes. While black holes pull everything inside them, white holes would do the opposite. They would push everything out. Nothing could enter a white hole, and anything already inside would be forced to leave. It's as if a white hole is the time-reversed version of a black hole. While black holes trap matter, white holes would push it away. However, white holes remain an idea, not a confirmed reality. No white hole has ever been seen. For them to exist, there would need to be very specific conditions that might not even be possible in nature. Some scientists suggest that white holes might appear as brief bursts of high energy, like gamma ray bursts or fast radio bursts, FARBs. But no such burst has yet been clearly identified as a white hole. Others believe that white holes might only exist for a very short time before quickly fading away, making them almost impossible to detect with our current instruments. Still, scientists are curious about them and continue to include white holes in models of the universe. Some ideas even suggest that black holes could eventually turn into white holes. Imagine that after a black hole forms, the matter inside could reach a point where instead of collapsing, it bounces back, pushing energy and mass outward. This idea, called the bounce theory, suggests that what we call a black hole could, over unimaginable periods of time, become a white hole. Some even wonder if white holes could be linked to the Big Bang, the birth of our universe. Instead of the universe being created from nothing, perhaps it came from the explosion of a white hole, born from a collapsed region of a past universe. Though this idea sounds intriguing, there is no clear proof. It remains a gentle, speculative idea, something to dream about and explore in the quiet corners of theoretical physics. Some scientists also think that white holes could be connected to wormholes, tunnels that might link far distant places in space. One side of a wormhole could act like a black hole, pulling things in, while the other side could be like a white hole, pushing things out. These ideas remain speculative, but they continue to inspire thoughts and dreams of what could lie beyond the stars. If white holes do exist, they would leave behind very clear signs. Unlike black holes, they would not trap light in an event horizon. Instead, they might radiate energy, or even erupt suddenly, like a volcano in space. However, no such eruptions have been seen, making it difficult to confirm their existence. Surveys continue looking for unusual signs that might match the predictions of white holes. Most of the energetic phenomena we see in space, like supernovae, quasars, and gamma-ray bursts, can be explained without white holes. This makes them less essential in current models of the universe. But some scientists believe that in isolated or extreme conditions, white holes could still exist. Their existence is mathematically possible, but that doesn't mean they definitely exist in nature. Many ideas in physics, though mathematically possible, may not appear in the real world. Still, studying these ideas pushes the limits of what we know and helps us understand the universe better. One of the challenges with white holes is something called entropy, a measure of disorder. A white hole would reduce entropy by pushing out ordered matter, which goes against a rule of physics called the second law of thermodynamics. This makes white holes unstable and unlikely to last. But there are models that allow for very short-lived white holes, suggesting that under certain circumstances they might exist briefly. While most scientists agree that white holes are unlikely to exist in the way we imagine them, there's still a possibility that they might have formed in the very early moments of the universe. Perhaps in the very first moments after the Big Bang, or in places with highly curved spacetime, white holes could have existed. But today, they would be invisible, hidden from our current instruments. In the future, new gravitational wave detectors could help us look for their faint signals, allowing us to study them indirectly. Until then, the idea of white holes remains an intriguing mystery. Despite the lack of evidence, they continue to be explored in theoretical physics. Studying them helps us push the boundaries of time, gravity, and space. Even if they don't exist, they help us refine our theories and help us imagine the possibilities that lie beyond the familiar. Now, let's look at something else that challenges our understanding of space: rogue planets. These are planets that don't orbit a star. Instead, they drift through interstellar space, wandering alone in the vastness of the galaxy. Some rogue planets might have formed around stars but were later ejected because of gravitational forces. Others may have formed on their own, like stars, but never reached the point of starting fusion. These rogue planets travel in the dark, unseen and unnoticed. The idea of rogue planets has fascinated scientists for a long time. Early models predicted that large disturbances in the gravitational forces around stars could send planets out into space, where they would drift alone. Some scientists believe that there could be billions of rogue planets in our galaxy, far outnumbering the stars themselves. Finding them is difficult though, because they don't emit any light. But using a technique called gravitational microlensing, scientists can detect rogue planets by the way their gravity bends the light from distant stars. This method doesn't rely on the planet shining, it only needs to affect the light coming from a distant star. Some rogue planets may even be Earth-sized, and they might retain a faint glow from the heat they still carry from their formation. Instruments like the WISE infrared telescope have already found some objects that might be rogue planets, but confirming them takes careful analysis of their mass, temperature, and movement. Many of these objects are still being studied as scientists continue to learn about them. Rogue planets challenge what we thought we knew about planets. Without a parent star, they don't have the seasons or warmth that regular planets experience. Some of them might even have atmospheres or internal heating, or maybe even moons. There's a chance, though slim, that these rogue planets could support life in extreme cases. Maybe under thick ice, one of these planets could have an ocean, hidden away from the harsh environment. If it did, it might support microbial life for billions of years, shielded from the dangers of radiation and cosmic threats. In science fiction, rogue planets are often portrayed as mysterious worlds, places of eternal night, refuge, or danger. In reality, these planets are quiet and cold, but they may be more common than we think. They provide us with a unique look at how planets form and survive in the harshest conditions. Though their exact origin is still debated, it's clear that they have a place in our understanding of the universe. Rogue planets might even help us understand the evolution of planetary systems in isolation. They don't follow the rules we once thought applied to all planets. The James Webb Space Telescope and other future missions may soon help us discover and study these wandering worlds. As we track their movements and study their atmospheres, if they have any, we'll continue to learn more about how planets can survive without a star. Some of these rogue planets may have passed through our solar system in the distant past, affecting the movement of asteroids or comets. Though no such planet has been identified yet, scientists believe that temporary encounters with rogue planets are a possibility. Searching for traces of rogue planets is a growing area of research, though it remains small. The exact number of these wandering planets across our galaxy is still a mystery. Most surveys tend to focus on larger or warmer objects, so the smaller, colder planets are likely more numerous, but harder to detect. To really understand how common these lonely planets are, scientists need to improve detection methods. With better tools and more data, we might begin to see these planets as an important part of our understanding of the galaxy. Rogue planets are a reminder that not all worlds orbit stars. Some drift alone, quiet and cold, carrying the secrets of their creation. They represent one of the most mysterious groups of objects in astronomy, waiting to be discovered. As our instruments improve, so will our ability to study these dark travelers, the true nomads of interstellar space. Some exoplanets orbit so close to their stars that their temperatures reach unimaginable levels. A group of these planets, known as ultra-hot Jupiters, have temperatures on their day size that exceed 2500 J. At these extreme temperatures, even metals like iron vaporize. As the planet rotates, this vapor cools down and condenses, falling as molten iron rain. A well-known example of this is WP76b, a gas giant located about 640 light-years from Earth. This planet is tidally locked, meaning one side is always facing the star while the other remains in darkness. On the day side, the heat turns iron into vapor, which is carried by winds to the cooler night side, where it condenses and falls as droplets of liquid metal. The contrast in temperatures between the day side and night side is over 1000 degrees, and the winds can reach thousands of kilometers per hour, redistributing the heat and metal vapor across the planet. The planet's weather system is based on metal instead of water, a fascinating and extreme form of atmospheric dynamics. WP76b is not the only planet with such extreme weather. Other ultra-hot Jupiters, like USP121b and Kelt 9b, show similar characteristics. Using telescopes like Hubble and Spitzer, scientists have detected metals like iron, titanium and magnesium in vapor form on these planets. These planets act as natural laboratories, helping us study atmospheric chemistry under the harshest conditions. To detect metal rain, scientists use a technique called transmission spectroscopy. As a planet passes in front of its star, the light from the star filters through the planet's atmosphere. Different atoms and molecules absorb different wavelengths of light, allowing scientists to infer the presence of metallic elements. It's a delicate process that requires careful timing and calibration. In the case of WP76b, scientists were able to observe differences between the morning and evening sides of the planet. Iron vapor was detected on the hot side, while condensation appeared on the cooler side, confirming the theory of iron rain. The planet essentially has a sunrise of vapor and a sunset of molten metal, a striking example of extreme atmospheric recycling. This discovery challenges what we know about planetary weather. On Earth, water drives the weather cycle, but on these exoplanets, it's metals that evaporate, condense, and fall back. This creates different atmospheric dynamics, such as vertical stratification, temperature inversions, and ionization. To model these atmospheres, scientists borrow tools from plasma physics and fluid dynamics, as the conditions are so extreme. The radiation environment around these planets is also intense. The planets are bombarded by powerful ultraviolet and X-ray radiation from their stars, ionizing parts of the atmosphere and creating metal-rich plasmas. This interaction between magnetic fields, radiation, and ionized gases can generate strong atmospheric currents, affecting heat transport and possibly triggering aurora-like phenomena. Some ultra-hot Jupiters might even lose their atmospheres over time, as the intense radiation strips away lighter elements, leaving only heavier components. This process could continue for billions of years, eventually reducing the planet to its core. Studying these extreme processes gives us a glimpse into planetary evolution under stress, helping us understand the diversity of exoplanet types. While these planets are inhospitable, they provide critical insights into exoplanet science. Their high temperatures make them easier to study, as their expanded atmospheres are more transparent. This makes ultra-hot Jupiters valuable targets for future telescopes like JWST. Their extreme conditions push our models of atmospheric chemistry and radiative transfer to the limit, refining our understanding of exoplanet atmospheres. They also help guide our search for Earth-like planets by revealing just how diverse planetary weather can be. Each new discovery adds another piece to the larger picture of planetary systems. Even if these planets are too hot to support life, studying them helps us understand what is physically possible in the universe. Exoplanets with iron rain may seem alien, but they follow the same fundamental physics as Earth. The extreme conditions just shift the elements involved, helping us deepen our understanding of how temperature, chemistry, and motion interact across the galaxy. These are not fictional worlds, they are real, observable, and part of the growing catalogue of planetary diversity. Another fascinating idea in space exploration is the concept of primordial black holes, which are hypothetical black holes that could have formed in the very early moments after the Big Bang. Unlike stellar black holes, which form from collapsing stars, primordial black holes might have formed from small fluctuations in the density of matter in the young universe. These fluctuations, tiny variations in mass, could have collapsed under their own gravity to form black holes. These primordial black holes could range in size from microscopic to thousands of solar masses. The idea was first proposed in the 1970s by physicists like Stephen Hawking, who explored how quantum fluctuations in the early universe might have seeded large structures. Some fluctuations might have been so intense that they created these compact objects, now known as primordial black holes, PBHs. PBHs are fascinating because they could offer clues about the universe just moments after the Big Bang. Their formation might reveal insights into inflation, the rapid expansion that shaped spacetime. Primordial black holes could also serve as probes of high-energy physics, providing valuable information far beyond what we can learn from particle accelerators. In this sense, PBHs could act as messengers from the universe's birth. One exciting possibility is that primordial black holes could explain some or all of dark matter. Since they don't emit light but do have mass, they meet the basic criteria for dark matter. Although surveys using microlensing, the bending of light from distant stars, haven't found enough evidence to confirm their existence, they remain a potential candidate for dark matter. Some black hole mergers detected by LIGO and Virgo have shown unusual properties, such as masses that don't match typical stellar black holes. This has led some scientists to propose that these mergers might involve primordial black holes. If this theory is confirmed, it would mark the first direct detection of primordial black holes. However, more data is needed to determine if their mass distribution truly differs from that of normal black holes. Primordial black holes could also have played a role in seeding the formation of galaxies. Massive PBHs in the early universe could have acted as gravitational wells, pulling in surrounding matter and triggering star formation. This idea could help explain how supermassive black holes formed so quickly after the Big Bang. While this process remains speculative, it is actively being explored. PBHs are also believed to evaporate through a process called Hawking radiation, where smaller black holes radiate energy and eventually disappear. This radiation might release bursts of gamma rays, neutrinos, or other particles, which could be detected by instruments like Fermi-LAT. If detected, this would confirm both the existence of PBHs and the theory of Hawking radiation. The mass of a primordial black hole depends on when it formed. Those formed earlier in the universe would be smaller, perhaps as small as asteroids. Others could be as large as stars. The variety in their size and mass makes it difficult to predict exactly what they are, but they offer rich possibilities for understanding the early universe. By matching the predictions of inflationary models with observational data, physicists can test theories about the origins of the universe. Primordial black holes could also leave detectable imprints in the cosmic microwave background. Their evaporation might cause slight changes in the temperature or polarization of the background radiation, which could hint at their existence. Missions like Planck and future probes like Lightbird are analyzing these subtle signals. If PBHs exist, they would be the oldest black holes in the universe, and discovering them would reshape our understanding of matter, gravity, and the early cosmos. Primordial black holes remain hypothetical, but every new piece of data brings us closer to understanding their role in the universe's formation. They are not just theoretical curiosities, but potential keys to the universe's deepest mysteries. Hypervelocity stars are stars that move so fast they can escape the gravitational pull of the Milky Way. Most stars orbit within galaxies at relatively steady speeds, but hypervelocity stars can reach speeds of over 1,000 kilometers per second, enough to leave the galaxy entirely. Their discovery in 2005 surprised astronomers, as no known mechanisms within regular stellar systems could explain such extreme speeds. Since then, dozens of these stars have been found, typically located in the outer halo of the galaxy. Their origins point to extreme processes near the galactic core. One main theory for their formation involves interactions with the supermassive black hole at the center of the Milky Way. When a binary star system passes too close to the black hole, the tidal forces can tear it apart. One star might be captured into a tight orbit, while the other is flung outward at incredible speeds. This gravitational slingshot effect efficiently produces the speeds needed to eject stars completely from the galaxy. Another possible mechanism is interactions in dense stellar clusters or supernova explosions within binary systems. If one star explodes, the remaining star may be propelled at high speed, depending on how the mass is distributed. These processes typically produce lower velocities than black hole interactions, but can still result in escape trajectories. Not all hypervelocity stars come from the galactic center. Some are believed to have originated in the galactic disk or even in dwarf galaxies. Each case reveals different histories of cosmic dynamics. Observing these stars can be challenging due to their distance and faintness. Many of them are detected far from the center of the galaxy, sometimes over 100,000 light-years away. Their movement is determined from precise measurements of radial velocity and proper motion. The Gaia Space Observatory has played a crucial role in identifying these stars, thanks to its precise mapping of stellar positions and motions. Some of these stars show clear paths that trace back to the galactic center. Interestingly, most confirmed hypervelocity stars are young, massive stars, which suggests that they were ejected not long ago. Their lifetimes are short, so they couldn't have travelled from the galactic center unless they were ejected recently. This aligns with models involving black hole interactions, which are thought to favour such stars. Older, less massive stars, while likely more numerous, are harder to trace. Their lower brightness makes detection more difficult. These fast-moving stars offer insights into the structure of the Milky Way's gravitational field. By analysing their paths, scientists can test models of the galaxy's potential, including the dark matter halo. Hypervelocity stars also serve as natural probes for studying the galaxy's outskirts, regions that are typically hard to observe. They pass through the galactic halo and intergalactic space, collecting information about the environments they pass through. Their motion is influenced by mass distributions far from the galactic disk. In rare cases, hypervelocity stars may travel between galaxies. If they were ejected early in the universe's history, they might now be drifting in intergalactic space, isolated from any stellar system. These rogue stars would be incredibly difficult to detect, but they represent a fascinating possibility. They challenge the idea that stars are always bound to galaxies. Some may even fall into other galaxies, eventually becoming part of a different stellar system altogether. One particularly interesting case is S5HVS1, a hypervelocity star discovered in 20s. It travels at about 700 kilometers per second and seems to have originated near the Milky Way's central black hole. Its speed and direction match predictions for black hole ejection. This provides strong observational evidence for the slingshot model and opens the door for more detailed reconstructions of interactions near the galactic center. Events like these help scientists test general relativity under extreme gravitational conditions. The ejection of stars doesn't just affect the individual stars themselves, It can also alter the dynamics of star clusters in the galactic center. Repeated ejections could carry away angular momentum or redistribute mass in complex ways. Over time, these processes shape the evolution of the Milky Way. Tracking hypervelocity stars helps us understand the galaxy as a whole. These stars are not just anomalies, they are key players in cosmic scale feedback. Some scientists wonder if hypervelocity stars could host planets, raising intriguing questions. Could a planet survive the ejection process? What would it be like to live on a world that's hurtling through intergalactic space? While these ideas are purely speculative, they highlight the vast variety of conditions that planetary systems might endure. If such a system were ever found, it would challenge our current models of planetary dynamics and survival. Future telescopes like the Vera Rubin Observatory will improve our ability to detect hypervelocity stars. With wider fields of view and better temporal resolution, they will be able to track fast-moving objects over time. Combining Gaia data with upcoming surveys will create more complete maps of stellar motion, potentially revealing not just more ejected stars, but also hidden structures like star clusters or black holes. Hypervelocity stars are more than just fast-moving objects. They're evidence of cosmic violence and gravitational extremes. They tell the story of interactions near black holes, of disrupted binary systems, and of powerful forces at the heart of our galaxy. Studying them helps us map the Milky Way, test models of stellar motion, and glimpse what happens when gravity is pushed to its limits. Neutron stars are another mysterious class of objects in the universe. These incredibly dense stars form when the core of a massive star collapses after a supernova explosion. A neutron star is so compact that it can pack more mass than the Sun into a sphere only about 20 kilometers across. The density is so extreme that atoms are crushed, and protons and their electrons combine to form neutrons. This makes neutron stars unique natural laboratories for studying physics under intense pressure and density. Some neutron stars seem to defy expectations. Observations have shown stars that are either too massive or too large to fit within current theoretical models. For example, some neutron stars exceed 2 solar masses, pushing the limits of our understanding of ultra-dense matter. Others spin so fast they approach the point where they would break apart. These anomalies suggest that our understanding of nuclear physics is incomplete at such extreme scales. One well-known example is PSR J0740+6630, one of the most massive neutron stars ever measured, with about 2.1 solar masses. If it were even slightly more massive, it might collapse into a black hole. Studying these extreme stars helps refine the nuclear equation of state, which describes the relationship between pressure, density, and temperature in dense matter. Some neutron stars, called magnetars, have magnetic fields trillions of times stronger than Earth's. These intense magnetic fields can distort the star's crust and produce bursts of X-rays and gamma rays. The origins of these fields are still debated, but they likely come from rapid rotation or unusual internal conditions. Magnetars represent the extremes of electromagnetic physics and provide valuable insights into forces rarely seen in nature. Neutron stars can also exhibit strange rotational behaviors. Pulsars, neutron stars that emit regular radio pulses, sometimes experience sudden changes in rotation, known as glitches. These glitches are thought to be caused by interactions between the superfluid interior and the solid crust. The internal dynamics may involve exotic particles and quantum fluids. These events offer a glimpse into matter under extreme conditions. In recent years, gravitational wave observatories like LIGO have detected neutron star mergers. These events not only confirm general relativity, but also provide valuable data on the internal structure of neutron stars. During these mergers, the stars deform and collapse, offering clues about their internal composition. The collision GW170817, for example, allowed scientists to study the stiffness of neutron star matter and test different models. These collisions are also responsible for creating heavy elements like gold and platinum. Some theories suggest that inside neutron stars, matter could reach even more exotic phases, like quark matter or a strange quark star. In these stars, neutrons may break down into their constituent quarks, creating a soup of fundamental particles. Although no definitive evidence has been found, unusual size and mass could indicate such interiors. If one were discovered, it would completely redefine what we consider a neutron star. A few neutron stars might also emit continuous gravitational waves, though none have been detected yet. If confirmed, these waves would provide a new way to study the internal structure and deformation of neutron stars. Detectors like LIGO and future instruments are being fine-tuned to look for these subtle signals, and if successful, they could open an entirely new window for astronomical research. Temperature measurements of neutron stars present some puzzles. Some cool down much faster than expected, while others remain warm for surprisingly long periods. These inconsistencies could involve neutrino emissions, superfluid transitions, or even interactions with dark matter. Observations from X-ray telescopes have helped refine models of neutron star cooling, with each case offering important clues about their internal makeup. Neutron stars in binary systems provide opportunities for precise mass and orbital measurements. When paired with white dwarfs or other neutron stars, they serve as natural test subjects for gravitational theories. Any deviations from expected orbital decay allow scientists to test general relativity with great accuracy. These observations help not only with understanding nuclear physics, but also with exploring theories of gravity and the curvature of space-time. With the help of new instruments like NICER on the International Space Station ISS, scientists can now measure neutron star radii and masses more accurately. This enables them to map the equation of state more directly. By comparing different neutron stars, researchers can begin to build a more comprehensive model of matter at nuclear and subnuclear scales. Each measurement provides another piece of the puzzle of ultra-dense matter. Neutron stars that defy current theoretical expectations aren't just anomalies, they represent the boundaries of physics. From massive outliers to magnetic monsters, they present conditions that no laboratory can replicate. By studying them, scientists refine their understanding of matter, gravity, and fundamental forces. Neutron stars are not only astronomical objects, they are physical experiments on a cosmic scale. Many galaxies are believed to contain large amounts of dark matter, a mysterious substance that doesn't emit or absorb light, but exerts gravitational influence. We infer its presence from how stars and gas move within galaxies. Normally, the rotation curves of galaxies flatten out at large distances, a sign of dark matter halos surrounding them. However, some galaxies seem to defy this rule. Observations have revealed rare cases of galaxies that appear to lack dark matter. One such example is NGC 2DF2, a faint galaxy located about 65 million light-years away. When scientists measured the velocities of star clusters inside it, they found them moving slower than expected, and the gravitational pull seemed too weak to require dark matter. This discovery challenged one of the most consistent features in cosmology. A follow-up study found another galaxy, NGC 2DF4, with similar properties, located near DF2. This raised the possibility that some galaxies could form without dark matter, or perhaps lose it over time through unknown processes. One idea suggests that tidal interactions with nearby galaxies could strip dark matter halos away, reshaping these galaxies. These galaxies belong to a class called ultra-diffuse galaxies, UDGs. They are large in size but contain fewer stars than typical galaxies. Some UDGs contain normal amounts of dark matter, while others appear to be lacking it, raising questions about how galaxy formation and dark matter interact in different environments. Scientists used integral field spectroscopy and globular cluster dynamics to study these galaxies. Instead of relying on starlight alone, they track the motion of star clusters orbiting the galaxy. The velocities of these clusters serve as markers of the galaxy's total mass. When the mass is too low to match expectations, it suggests a lack of dark matter. Some researchers proposed that measurement errors could explain the results, suggesting that the galaxies might be closer than originally thought, making them appear less massive. Others questioned the assumptions made about how mass is distributed, or how star clusters are bound. However, independent teams using different methods have confirmed the low dark matter content in these galaxies. While there are still uncertainties, the evidence is becoming stronger. If these galaxies really lack dark matter, it would force us to reconsider how we model galaxy formation. Traditional models assume that dark matter is essential for forming galaxies. Without it, gas should struggle to collapse into stable star-forming structures. These galaxies might represent a rare evolutionary path or offer a clue to unknown physics. Their existence calls for better theoretical explanations. Alternative gravity theories such as modified Newtonian dynamics, MOND, have also come under scrutiny. If some galaxies really lack dark matter and still show normal dynamics, it challenges the MOND model. But if anomalies arise in galaxies that should have dark matter, it could lend support to alternative models. These rare galaxies provide a testing ground for different ideas about gravity, mass, and cosmic structure. Understanding how these galaxies formed may involve baryonic feedback, the effects of supernova explosions, stellar winds, and radiation. Powerful outflows could theoretically expel gas, influencing the balance of gravitational forces and possibly separating baryonic matter from dark matter. Simulations that include this feedback have shown that such outcomes are possible, though matching these scenarios with observed galaxies remains difficult. The environment around these galaxies may offer more clues. Both DF2 and DF4 are near a large elliptical galaxy, NGC 152. Tidal interactions, ram pressure stripping, or gravitational harassment could have distorted or depleted their dark matter halos. If this is true, these galaxies may have been reshaped by their environment, not formed in isolation. This explanation is consistent with the models of galaxy clusters and their dynamics. Future observations using the James Webb Space Telescope, JWST, and next-generation spectrographs will refine distance measurements and stellar population models. If more galaxies without dark matter are discovered, it will strengthen the case for this rare subclass of galaxies. Each discovery adds new constraints on how galaxies evolve and how matter is distributed across space. While these galaxies are statistical outliers, they are scientifically crucial. Galaxies without dark matter remain controversial, but they prompt deeper questions. What role does dark matter really play in galaxy formation? Can galaxies survive without it? And how do rare objects like DF2 fit into the grand puzzle of the universe? Whether these galaxies are anomalies or hints of new physics, they push the limits of our current understanding. In the world of vacuum fluctuations, things aren't quite as empty as they seem. In classical physics, a vacuum is thought to be the absence of matter, an empty void. But in quantum field theory, even the most perfect vacuum is far from empty. It's filled with energy fluctuations that spontaneously create virtual particles, popping in and out of existence. This dynamic activity in the vacuum is a key part of the universe's structure. The Heisenberg uncertainty principle tells us that energy and time cannot both be precisely measured, allowing energy to briefly appear as particle-antiparticle pairs. These particles are called virtual particles, and while they cannot be directly observed, they influence real-world physical processes. One well-known example of this is the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience a force that pushes them together. This is due to quantum fluctuations that exclude certain wavelengths of virtual particles between the plates, creating a net force. It's a measurable effect of vacuum energy, showing that even empty space is active and dynamic. Another example is the Lamb shift, an energy correction observed in hydrogen atoms. It occurs because of interactions between electrons and vacuum fluctuations in the electromagnetic field. This small shift in energy further proves that quantum effects extend even into the most empty spaces. In cosmology, vacuum fluctuations may have played a key role during the inflationary period, when the universe expanded rapidly right after the Big Bang. Tiny quantum fluctuations were stretched to cosmic scales, creating the density variations that eventually formed galaxies. What started as microscopic uncertainty became the blueprint for the structure of the universe. Vacuum energy is also linked to the cosmological constant, a term in Einstein's equations that explains the accelerated expansion of the universe. Observations show that space is expanding faster over time, and vacuum energy is one potential explanation for this. However, the predicted value of vacuum energy from quantum theory is much larger than what we observe, creating a discrepancy known as the cosmological constant problem. Virtual particles also play a role in Hawking radiation, the theoretical process by which black holes evaporate. Near the event horizon, quantum fluctuations separate particle pairs, with one particle falling into the black hole and the other escaping. This reduces the black hole's mass over time, providing evidence that even the strongest gravitational fields are influenced by quantum effects. In particle physics, vacuum fluctuations are also considered in calculations using Feynman diagrams, helping us understand how energy and particles behave under different conditions. The loops in these diagrams depict virtual particles that briefly exist and influence outcomes. Their contributions are crucial in making accurate predictions in quantum electronics and various other fields. Without considering vacuum fluctuations, both theory and experiment would diverge. The properties of the vacuum also play a significant role in material science. In superconductors and other quantum materials, these fluctuations can impact electron behavior and phase transitions. This field of research investigates how vacuum energy might be manipulated at the nanoscale, potentially leading to breakthroughs in quantum computing or energy storage, depending on how these subtle forces are harnessed. Efforts to measure vacuum energy with higher precision include experiments in space, where external forces are minimized. Projects like LISA and other gravitational wave detectors could eventually detect the minute distortions caused by vacuum fluctuations. Laboratory-scale setups are also advancing with precise measurements of atomic transitions and tiny forces. These methods aim to link theory with direct observation. Although invisible and transient, vacuum fluctuations may be fundamental to the very structure of reality. Every force, particle, and interaction in the universe is built upon this restless foundation, challenging the classical notion of emptiness and replacing it with a vibrant field of potential. Nature does not simply abhor a vacuum, she never allows one to truly exist. In quantum physics, empty space is a myth. The vacuum is teeming with energy, potential, and structure. Understanding its behavior is key to unifying quantum mechanics, gravity, and cosmology. The more we uncover about it, the more we realize that everything might have emerged from nearly nothing, and that nothing was never truly void. Supernovae, which explode sooner than expected, are powerful events marking the death of certain stars. Normally, these explosions follow predictable life cycles based on the star's mass and composition. Type Ia supernovae are generally thought to occur when a white dwarf accumulates enough mass to reach the Chandrasekhar limit, about 1.4 times the mass of the Sun. Once this threshold is exceeded, runaway nuclear fusion ignites, causing the star to explode. This process was long considered well understood and consistent. However, recent discoveries have challenged this expectation. Some supernovae seem to explode before the white dwarf reaches the Chandrasekhar limit. These sub-Chandrasekhar events raise questions about what might trigger an explosion prematurely. In these cases, the explosion might be due to a different mechanism, perhaps a surface ignition that sparks the rest of the star. This early detonation could disrupt the white dwarf without needing to achieve the critical mass. One hypothesis is the double detonation model. In this scenario, a thin layer of helium accumulates on the white dwarf's surface. Once enough helium is present, it ignites explosively, sending shockwaves into the core, triggering carbon fusion deep inside, and leading to a full-scale supernova. This model bypasses the need to reach the Chandrasekhar limit and offers an explanation for early explosions. Observational evidence increasingly supports this model. These premature supernovae show slightly different spectra and light curves compared to standard type Ia events. They may, for instance, produce more calcium and less nickel than expected. The timing of the peak brightness and the shape of the decline can provide valuable clues about the explosion mechanism. Telescopes like Kepler and the Zwicky Transient Facility are used to detect these events early and record their development in detail. Another possible trigger is white dwarf collisions. In dense stellar environments or tight binary systems, two white dwarfs may spiral together and merge violently. The merger itself could create conditions hot and dense enough to initiate fusion. If the combined mass remains below the Chandrasekhar limit but the merger is violent enough, an early explosion may occur. This could explain some subluminous or fast-evolving supernovae. Premature explosions are significant for understanding cosmic distance measurements. Type Ia supernovae serve as standard candles for measuring the universe's expansion. If some of these explosions behave differently, it could introduce subtle errors in cosmological calculations. Therefore, distinguishing between standard and early triggered events is vital for precision cosmology. Researchers now classify subtypes of Type Ia supernovae to track these variations. Some premature explosions may be due to mass transfer in binary systems. If a companion star donates material to a white dwarf at an unstable rate, it could trigger localized fusion before the total mass threshold is reached. This type of asymmetric ignition can lead to uneven explosions, influencing the shape and brightness of the event. These interactions also affect the composition and velocity of the ejected material. High-speed imaging has detected early shock signatures in some supernovae. In a few instances, astronomers observed ultraviolet flashes preceding the main light curve. These flashes point to surface ignitions or interactions with a nearby companion, both consistent with early explosion models. Observations from telescopes like Hubble and Swift have been crucial for detecting these rapid, transient features. Simulations of sub-Chandrasekhar explosions provide insights into nucleosynthesis, the creation of new elements. Different initial conditions alter the formation of elements such as iron, nickel, and silicon during the explosion. These models must be tested against actual observed spectra. As models and data gradually converge, our understanding of early detonation pathways continues to improve. Premature explosions also affect the surrounding interstellar medium by ejecting material more asymmetrically, creating irregular shock fronts. These shock fronts can shape the formation of nearby stars, or trigger turbulence in the galactic environment. The structure and velocity of supernova remnants offer clues about the explosion dynamics. X-ray observations help map these remnants in 3 dimensions. Unusual supernovae are being detected more frequently due to automated sky surveys. Instruments like Pan-STARRS and LSST are identifying transient events at an unprecedented rate. This larger dataset allows astronomers to identify patterns, outliers, and entirely new classes of stellar deaths. Some premature explosions might belong to completely new categories that do not fit within existing classification systems. The discovery of early supernova explosions highlights the diversity of stellar deaths. Not all stars follow traditional rules. By studying these exceptions, astronomers refine models of stellar evolution, fusion physics, and cosmology. Each early detonation adds a piece to the puzzle of how stars live and die. The phantom rotation of galaxies is an intriguing phenomenon. When astronomers first measured how stars move within galaxies, they noticed an anomaly. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, similar to planets in the solar system. However, observations showed that rotation speeds remain flat or even rise at large distances. This unexpected behavior is known as the galaxy rotation curve problem. It is one of the clearest indicators that something invisible is influencing gravity. To explain this anomaly, scientists proposed the existence of dark matter, an invisible form of mass that does not emit light but exerts gravitational force. If galaxies are surrounded by massive dark matter halos, it could explain the flat rotation curves. The stars are not rotating too fast. They are simply moving under the influence of extra unseen mass. This concept became a cornerstone of modern cosmology. This effect is most noticeable in spiral galaxies, where rotation curves have been studied extensively. Measurements show that stars orbit at nearly constant speeds far beyond the visible edge of the galaxy. This suggests that most of the galaxy's mass is contained in a halo extending well beyond what can be observed. These halos are believed to consist of cold, non-interacting particles that only affect the universe through gravity. The phantom rotation has been confirmed across thousands of galaxies. Surveys like the Sloan Digital Sky Survey and the HI Nearby Galaxy Survey have measured rotation curves in various systems. Whether large or small, isolated or clustered, galaxies consistently show this anomalous behavior. The universality of this phenomenon strengthens the case for dark matter as a key component of the cosmos. Alternative explanations, such as modified Newtonian dynamics, MOND, suggest that gravity behaves differently at very low accelerations. Instead of invoking unseen matter, MOND modifies the laws of motion, While MOND can replicate some galactic rotation curves, it struggles to explain galaxy clusters, gravitational lensing, and the cosmic microwave background. Most evidence still supports the dark matter hypothesis. The phantom rotation is not just a curiosity, it has cosmological implications. The distribution and behavior of dark matter affect how galaxies form, interact, and evolve. It also influences large-scale structures like filaments and voids in the cosmic web. Understanding galaxy rotation helps improve simulations of the early universe and test predictions of cosmological models. Some galaxies display rotation curve anomalies that challenge even dark matter models. For instance, a few low-surface brightness galaxies have rotation curves that rise more steeply or behave irregularly. These exceptions help refine our understanding of both baryonic physics and dark matter interactions. They may point to variations in halo shapes, past mergers, or gas dynamics. Simulations like Illustris and Eagle model galactic formation, using both dark matter and baryonic matter. These projects illustrate how galaxies develop their rotation profiles through intricate interactions. Feedback from star formation, supernovae, and black holes all contribute to forming the final rotation curves. Matching simulated galaxies with actual ones is a crucial test for the models. Rotation curves are also instrumental in mapping the mass-to-light ratio in galaxies. By comparing visible matter to inferred mass, astronomers estimate the presence of dark matter. These ratios vary by galaxy type and environment, offering insights into the distribution of dark matter. Some dwarf galaxies are almost entirely made up of dark matter, while others show a more balanced mix. The stability of galactic disks depends on the underlying mass distribution. Without adequate dark matter, many spiral galaxies would be unstable. The added gravity from dark matter halos helps maintain the thin rotating structure. It also protects galaxies during mergers and interactions, allowing them to survive violent events without disintegrating. Future missions like the Euclid Space Telescope will provide more precise mapping of dark matter using gravitational lensing. This technique measures how mass bends light from background sources, revealing mass distributions directly. Combining lensing data with rotation curves will help create a more complete picture of galactic structure, and may even test alternative gravity theories in new environments. Phantom rotation continues to be one of the most compelling pieces of evidence for dark matter. Though invisible, its influence shapes galaxies, structures, and the dynamics of the universe. Understanding why stars do not slow down is key to understanding the composition of most of the universe. What occurs inside a black hole? Black holes form when a massive star collapses under its own gravity at the end of its life. The collapse compresses the star's core into an incredibly dense region where gravity is so strong that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. Inside, space and time behave differently from anywhere else. Classical physics breaks down near the center. According to general relativity, the mass of a black hole is concentrated in a single point of infinite density, known as the singularity. At this point, the laws of physics cease to operate. The curvature of space-time becomes infinite, and no model can describe what occurs there with certainty, making black holes one of the greatest puzzles in theoretical physics. What exists at the singularity remains unknown. As matter falls toward the event horizon, it accelerates and is stretched by tidal forces. This process, known as spaghettification, elongates objects as gravity pulls more strongly on the nearest parts. Outside observers see the infalling matter slow down and fade, appearing to freeze at the event horizon. However, the falling object would pass through in finite time, experiencing extreme gravitational conditions. The inner structure of a black hole depends on whether it is rotating. A rotating black hole, described by the Kerr metric, may have a ring-shaped singularity and a region called the ergosphere. In this zone, space-time is dragged around by the black hole's spin. This leads to theoretical possibilities like energy extraction through the Penrose process. The rotation affects how matter and radiation behave near the horizon. Quantum mechanics adds further complexity. According to the no-hair theorem, black holes can be completely described by just three properties: mass, spin, and charge. All other information is thought to be lost, leading to the black hole information paradox. If information is destroyed inside a black hole, it conflicts with principles of quantum theory. This tension between relativity and quantum mechanics remains unresolved. One attempt to reconcile these ideas involves quantum gravity. Theories like string theory and loop quantum gravity aim to describe what happens at the Planck scale inside black holes. Some models suggest that the singularity could be replaced by a quantum core or a bounce. These ideas are still theoretical and untestable, but they provide ways to avoid infinite densities and preserve information. Black holes might emit radiation due to quantum effects near the event horizon, known as Hawking radiation. Virtual particles near the horizon can become real if one falls into the black hole while the other escapes. This leads to a gradual loss of mass and energy from the black hole. Over time, this radiation could cause the black hole to evaporate completely, although this process has never been directly observed. The interior of a black hole is unobservable from the outside. The event horizon acts as a one-way boundary, with no signals or light able to escape to reveal what's inside. All knowledge of internal behavior comes from theoretical models and indirect effects. This makes black holes natural laboratories for testing the limits of physics. What happens beyond the event horizon may require a new unified theory. Some models predict that black holes might harbor firewalls, hypothetical zones of intense energy at the event horizon. If true, this would contradict the smooth passage predicted by general relativity. The firewall hypothesis is controversial and challenges the idea that falling into a large black hole would feel uneventful. It reflects the unresolved tension between quantum principles and space-time geometry. Black holes might also play a role in the early universe. Primordial black holes, if they exist, could have formed shortly after the Big Bang. These might serve as dark matter candidates or seeds for supermassive black holes. Their interiors, if different from stellar collapse black holes, could reveal new aspects of early universe physics. However, this is speculative due to the lack of observational evidence. At the centre of the Milky Way lies Sagittarius A, a supermassive black hole with more than 4 million solar masses. Observations of stars orbiting it confirm the presence of a powerful gravitational source, yet even here the interior remains hidden. The Event Horizon Telescope's images provide insight into the shadow but not the core. Exploring the inside remains one of physics' ultimate frontiers. Until a quantum theory of gravity is confirmed, what happens inside a black hole remains a mystery. General relativity predicts singularities, while quantum theory suggests something else. The true structure of the interior, whether smooth, chaotic, or something unimaginable, is still unknown. Quark stars, a form of matter never before seen, might exist. When a massive star explodes in a supernova, its core can collapse into a neutron star, a dense sphere of neutrons tightly packed under immense pressure. Neutron stars represent one of the densest known forms of matter. However, under even greater pressure, neutrons may break apart into quarks, the fundamental particles that make up protons and neutrons. This could lead to a new class of objects, quark stars. Quarks are the smallest known building blocks of matter. Typically confined inside particles like protons and neutrons, quarks are bound together by the strong nuclear force. However, under extreme conditions, quarks may become deconfined and exist freely in a state known as quark-gluon plasma. This state existed shortly after the Big Bang and can be recreated in particle accelerators for brief moments. In stars, it might be stable over astronomical timescales. If the pressure inside a neutron star becomes high enough, the dense core may transition into quark matter, turning the star into a hybrid star with a neutron outer shell and a quark core. If the transition affects the entire object, the star becomes a strange quark star, composed mostly of up, down, and strange quarks. These hypothetical stars would be smaller and denser than neutron stars. Quark stars might be the missing link between neutron stars and black holes. Their extreme density would make them compact enough to resemble black holes from a distance, but without an event horizon. Observations of ultra-dense stars with unusual mass-radius relationships might hint at the presence of quark matter. Astronomers are searching for these signals using X-ray timing and gravitational wave data. Some neutron stars have been observed with masses and radii that are difficult to explain with standard neutron star models. These anomalies could indicate the presence of exotic phases of matter. Quark matter is a leading candidate, and theoretical models are being adjusted to match observations. If confirmed, this would provide direct evidence of a new state of matter in the universe. Quark stars might also rotate differently than neutron stars. Their moment of inertia and internal fluidity could affect how they spin and how they emit gravitational waves. Timing pulsars, rapidly rotating neutron stars could offer clues. Any deviations in their spin behavior or glitch patterns might suggest exotic cause. Advanced radio telescopes are monitoring these subtle changes. The surface of a quark star might behave differently too. Some models suggest it could be bare without a traditional crust or covered by a thin electron layer. This would affect the way the star cools, emits radiation, and interacts with its surroundings. Unusual thermal signatures or bursts of gamma rays could suggest the presence of such surfaces. Detecting these would require high-resolution instruments. Quark stars may also be more stable than neutron stars under certain conditions. Some theories suggest that strange quark matter is the most stable form of matter, even more stable than atomic nuclei. If this is correct, any neutron star reaching the right conditions might naturally collapse into a quark star. This conversion would release energy and dramatically alter the star's internal structure. In extreme cases, quark matter could form droplets known as strangelets, which might be ejected during collisions. If strangelets are stable, they could travel through space and potentially trigger phase transitions in other neutron stars. While no strangelets have been detected yet, their discovery would significantly impact nuclear physics. This idea remains speculative but is actively explored in high-energy research. The formation of quark stars might also be tied to the collapse of supermassive neutron stars. If the mass is too high for a stable neutron star but too low for a black hole, a quark star might form as a temporary phase. Observing the aftermath of such events through gravitational waves or neutrino bursts could offer new evidence. Instruments like LIGO and IceCube may help detect these rare transitions. Simulating quark star formation requires complex models of quantum chromodynamics, the theory governing quark behavior. These simulations are computationally intensive but essential for predicting what astronomers should look for. Matching theory with observation is still in its early stages, but progress is accelerating. Each new data point brings us closer to confirming or ruling out their existence. Quark stars remain hypothetical, but they represent one of the most exciting frontiers in astrophysics. If proven to exist, they would broaden our understanding of matter, gravity, and the life cycles of stars. The cosmological principle assumes that the universe is isotropic and homogeneous, meaning it appears the same in all directions and from any location. This principle forms the foundation of most cosmological models and simplifies equations describing the expansion of space. However, observations of the cosmic microwave background, CMB, have raised questions about this assumption. A strange alignment in the data suggests the presence of a preferred direction, often referred to as the axis of evil. This anomaly was first noticed in data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite. Instead of a random uniform distribution of temperature fluctuations in the CMB, scientists found a large-scale alignment of low-order multipoles. These modes seem to point in a specific direction in the sky. This violates the expectation of isotropy and has puzzled cosmologists for years. The term axis of evil reflects both the surprise and discomfort it caused. If the universe has a built-in axis of symmetry, it would challenge the standard cosmological model. The inflationary theory, which describes the rapid expansion of the universe just after the Big Bang, predicts randomness at large scales. The observed alignment suggests that something else might be influencing the structure of space. Some researchers propose that the alignment could be a statistical fluke, an unlikely coincidence amplified by human pattern recognition. However, repeated observations and independent analyses have shown that the feature persists. The probability of such an alignment occurring by chance is low, though not zero. This keeps the debate alive in the scientific community. Other theories suggest that the anomaly might come from foreground contamination, interference from our galaxy or the solar system. Dust, cosmic rays, or local structures could introduce noise into the measurements. but multiple attempts to clean the data still reveal the same alignment, suggesting that the axis is either real or the result of some unknown systematic error. If the axis is real, it could point to new physics. Some speculative models involve topological defects from early universe phase transitions. Others suggest that the universe might have a global rotation or a non-trivial shape, like a torus. These ideas are difficult to test, but they provide possible explanations consistent with the observed large-scale alignment. There are also theories involving multiverse scenarios, where collisions between our universe and another could leave an imprint in the CMB. A slight asymmetry in the initial conditions of our universe might stretch across space-time. Although these ideas remain speculative, they are part of ongoing efforts to explain the anomaly without abandoning current physics. Another possible cause is anisotropic inflation, a variation of the inflationary model where the expansion rate varies slightly with direction. If inflation wasn't perfectly uniform, it could imprint a large-scale asymmetry that is now detectable in the CMB. This would preserve the general inflationary framework while allowing for directional features. Some large-scale surveys of galaxies and quasars have also hinted at similar preferred directions. Patterns in galaxy spin orientation or quasar polarization may align with the same axis found in the CMB. If confirmed, these correlations would strengthen the case for a cosmic asymmetry. More data from future telescopes like the Vera Rubin Observatory will be crucial in testing these theories. Despite its name, the axis of evil does not imply any dramatic consequences for life or local structures. The universe remains mostly uniform on small scales, and gravitational laws still apply as expected. However, the anomaly may affect how we understand the overall shape and origin of the cosmos, which is why it continues to attract attention. The presence of an axis of symmetry could have implications for the cosmological constant, dark energy, and the fate of the universe. If space has a built-in directionality, it could influence how expansion occurs over time. Even tiny deviations from isotropy can accumulate over billions of years, which is why precision matters in these measurements. Until more evidence emerges, the axis of symmetry remains one of the most intriguing anomalies in cosmology. Whether it's an artifact or a signal of deeper laws is still unknown, but its persistence across datasets makes it impossible to ignore. Relativistic jets that span entire galaxies are high-speed streams of particles ejected from the centers of galaxies, often traveling at speeds close to the speed of light. These jets originate from the vicinity of supermassive black holes found in active galactic nuclei, AGN. As matter spirals into the black hole, it forms an accretion disk. Magnetic fields twist and accelerate particles along the poles, launching them outward as jets. These jets are composed primarily of electrons, positrons, and magnetic fields. While their exact composition may vary, they are collimated into narrow beams that can extend across thousands or even millions of light-years. Some jets are visible in radio wavelengths, while others emit X-rays and gamma rays. The most extreme examples can outshine their host galaxies in certain bands. These jets are powered by the conversion of gravitational energy into kinetic energy. As material falls inward toward the black hole, it heats up and generates intense magnetic turbulence. The rotation of the black hole and its accretion disk helps launch and focus the jets. The process is described by models like the Blanford-Znaeck mechanism, which relies on magnetic field lines anchored to the spinning black hole. Relativistic jets are often observed in radio galaxies and quasars. In radio images, they appear as long, symmetrical structures with bright cores and extended lobes. These lobes form when the jets collide with intergalactic material, slow down and inflate large clouds of plasma. The structure and brightness of these jets can reveal details about the environment they pass through. Some jets are one-sided due to relativistic beaming. When a jet moves nearly toward us, its light is Doppler boosted, appearing much brighter than the counterjet. This makes it difficult to detect both sides equally, depending on the orientation. Measuring jet brightness and asymmetry helps estimate their speed and angle relative to Earth. The lengths of these jets are enormous. In some cases, they stretch over 1 million light-years from the central black hole. The galaxy Hercules A and the Cuissar 3C273 are prime examples of such massive structures. These jets affect their host galaxies and surrounding regions by heating interstellar gas and regulating star formation. Jets can vary in stability. Some appear straight and consistent, while others wobble, twist, or show knots of brighter emission. These patterns may result from precession, magnetic instabilities, or changes in the accretion rate. In some systems, the jet may even shut off temporarily and then restart, creating disconnected structures. One remarkable phenomenon is superluminal motion, where parts of the jet appear to move faster than light. This is an optical illusion caused by the jet moving at near light speed at a small angle toward the observer. The light from successive positions arrives so closely spaced in time that the motion seems faster than light. This is a striking confirmation of relativistic effects. Relativistic jets are also linked to feedback processes in galaxy evolution. As the jets inject energy into the surrounding gas, they can suppress or stimulate star formation. This helps regulate the growth of the galaxy in its central black hole. Observing these effects across cosmic time offers insight into how galaxies have evolved alongside their active cores. Jets can transport energy over vast distances with minimal loss, making them highly effective at influencing large regions of space. They also serve as cosmic laboratories for studying particle acceleration, magnetic fields, and high-energy physics. Observing synchrotron radiation from jets helps measure the strength and orientation of magnetic fields. Gamma-ray bursts, GRBs, are another context in which relativistic jets appear. In these short-lived but intense explosions, jets are launched from collapsing stars or neutron star mergers. Although smaller in scale than galactic jets, GRBs exhibit similar physics, featuring highly collimated ultra-relativistic outflows that emit intense radiation. Both scenarios test extreme conditions of matter and energy. Relativistic jets remain among the most spectacular and energetic phenomena in the universe. By studying them, scientists gain valuable insights into black hole physics, galaxy evolution, and the role of feedback mechanisms on cosmic scales. Intergalactic space is often imagined as empty and silent, and in many ways it is. The vast distances between galaxies contain very few atoms per cubic meter, creating a near-perfect vacuum. Sound, which requires a medium to travel through, cannot propagate in such an environment, resulting in literal silence. There are no sound waves, no vibrations, only radiation and particles drifting silently. The intergalactic medium, IgM, contains trace amounts of ionized hydrogen and helium left over from the early universe. These particles are incredibly scarce, with densities sometimes as low as 1 atom per cubic meter. Temperatures in the IgM can vary widely, ranging from millions of degrees in galaxy clusters to near absolute zero in more isolated regions. Despite the heat, the lack of particles prevents heat conduction and sound transmission. Although silent in terms of sound, intergalactic space is not entirely empty. It is threaded with cosmic filaments, vast structures made of dark matter and hot gas that connect galaxy clusters. These filaments are part of the cosmic web, the large-scale structure of the universe. Matter moves slowly along these threads under the influence of gravity, shaping the distribution of galaxies. Some regions between galaxies, especially in voids, are even more desolate. Cosmic voids can span hundreds of millions of light-years and contain extremely low matter density. These zones are so empty that galaxies and intergalactic gas are almost entirely absent. Studying these voids helps scientists understand dark energy and the uniformity of cosmic expansion. The silence of intergalactic space also provides an ideal environment for astronomical observations because it lacks atmospheric distortion, magnetic fields, or noise from nearby stars. Deep space observations made from this vacuum can detect extremely faint signals, which is why spacecraft like the James Webb Space Telescope benefit from observing in space rather than from Earth. Despite the silence, this space is filled with background radiation. High-energy cosmic rays, gamma rays from distant events, and the cosmic microwave background all travel through this void. These forms of energy are not audible, but can be detected with specialized instruments. They serve as silent messengers of violent and ancient processes across the cosmos. The boundaries of galaxies and galaxy clusters are marked by shockwaves in the IGM, particularly during mergers or interactions. These events can heat the surrounding gas and inject turbulence. However, these shocks occur in such thin gas that they are undetectable to human senses. Even the most energetic collisions remain entirely silent in the traditional sense. Radio telescopes can detect emissions from neutral hydrogen in intergalactic space, especially in the early universe. This helps map the distribution of matter over billions of years, but again, what is detected is radiation, not sound. The silence remains, even in the presence of detectable signals. Intergalactic space is also where dark matter exerts much of its gravitational influence. Although it cannot be seen or heard, its effects are measurable through gravitational lensing and galaxy motion. This invisible structure organizes the cosmos silently, providing scaffolding for the visible universe. Its presence underscores how much happens without any sensory signal. As spacecraft travel farther from Earth, they enter regions that increasingly resemble this intergalactic quiet beyond the solar wind in the helipause. Space becomes cleaner and colder. Voyager 1 has already crossed this boundary and entered interstellar space, a step closer to the true silence between galaxies. Its instruments detect only faint plasma oscillations and particle streams. This silence also limits communication. Future intergalactic missions would rely entirely on electromagnetic signals, which take millions of years to cross the distances between galaxies. Any message sent would be delayed and attenuated. In that sense, the silence is not just physical but communicative, a consequence of vast spatial and temporal separation. While intergalactic space is silent in sound, it is full of invisible structure and energy. Radiation, gravity, and particle motion continue without producing any noise we can hear. It's an environment where silence is not emptiness, but a different mode of cosmic activity. The cosmic microwave background, CMB, is a faint glow of radiation that fills the universe, coming from every direction in the sky. It is the remnant heat from the Big Bang cooled and stretched over 13.8 billion years as space expanded. Discovered in 1965 by Penzias and Wilson, the CMB provided definitive evidence for the Big Bang model. It is the oldest light we can observe. This radiation was released about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen. Before that, photons were constantly scattered by free particles, making the universe opaque. Once atoms formed, photons could travel freely, an event known as recombination. The light from that era now appears in the microwave range due to cosmic redshift. The CMB has an incredibly uniform temperature of 2.725 K, with slight variations on the order of millionths of a degree. These tiny fluctuations contain critical information about the early universe. They reveal the seeds of future galaxy formation and the density variations caused by quantum fluctuations during inflation. Satellites like COBE, WMAP, and Planck have mapped these patterns in detail. The CMB is not a sound wave, but it represents a kind of fossil record of sound. In the early universe, pressure waves moved through the hot plasma, creating oscillations in density and temperature. These acoustic waves left imprints in the CMB. The resulting patterns, known as baryon acoustic oscillations, still influence the distribution of galaxies today. The angular power spectrum of the CMB reveals peaks that correspond to these acoustic waves. Each peak carries information about the universe's curvature, density, and composition. The position and height of these peaks help determine the proportion of dark matter, ordinary matter, and dark energy. Precision measurements have allowed cosmologists to refine the standard model of cosmology. The CMB also exhibits polarization, caused by the scattering of photons during the recombination era. This polarization contains subtle clues about the gravitational waves that may have rippled through space during inflation. Detecting these patterns, especially the B-mode polarization, is a major goal of ongoing experiments. It could confirm the existence of inflation and shed light on quantum gravity. Despite its uniformity, the CMB shows a few anomalies. These include the cold spot, large-scale alignments, and hemispheric asymmetry. While some may be statistical artifacts, Others suggest deeper cosmic phenomena or unknown physics. These irregularities remain subjects of intense study and debate. The CMB has a blackbody spectrum, one of the most perfect ever measured in nature. It closely matches theoretical predictions, confirming our understanding of thermal radiation in a cooling universe. Its peak wavelength corresponds to microwave frequencies, making it detectable by specialized instruments from both space and ground-based observatories. Mapping the CMB has required removing foreground signals, like galactic dust and synchrotron emission. Advanced techniques allow astronomers to isolate the true cosmic signal from local interference. The Planck mission has provided the most detailed map to date, revealing not just temperature, but also polarization and spectral distortions. Future missions aim to refine CMB measurements even further. Projects like Lightbird and CMBS-4 will attempt to detect even fainter features. These could reveal non-Gaussianities or signatures of exotic particles in the early universe. Improving resolution and sensitivity will push the limits of observational cosmology. The CMB continues to be a cornerstone of cosmological research. Its discovery transformed our understanding of the universe's origin, structure, and fate. By studying its fine details, scientists explore conditions that existed when the universe was less than 500,000 years old. The background radiation is not truly a whisper in sound, but in information. It quietly encodes the universe's earliest story, waiting to be interpreted through the language of physics and light. Comets are icy bodies from the outer regions of the solar system, typically following elliptical orbits that bring them close to the Sun before flinging them back into deep space. Most comets originate from two main sources, the Kuiper belt beyond Neptune and the more distant Oort cloud, which may extend halfway to the nearest stars. Their paths are shaped by gravity, but some comets have trajectories that defy conventional orbital mechanics. A few of these objects display hyperbolic or nearly parabolic orbits, suggesting they are not bound to the Sun. Rather than returning after a lengthy orbit, they pass through the solar system once and then never return. A notable recent example is Oumuamua. Discovered in 2017, it was the first known interstellar object observed passing through our planetary neighbourhood with a speed and path that couldn't be explained by solar system origins. Its trajectory was not solely influenced by gravity. Observations indicated non-gravitational acceleration, potentially due to outgassing or other forces. However, unlike typical comets, Oumuamua showed no visible tail or coma. Its unusual shape, possibly flat and elongated, and its tumbling motion added to the mystery. Scientists proposed various models ranging from nitrogen icebergs to exotic cosmic fragments. In 2019, another interstellar object, 2I Borisov, was detected. It had a more typical comet-like appearance with a visible coma and tail, suggesting it was composed of ices, similar to those found in solar system comets. Its hyperbolic orbit confirmed its interstellar origin, and its composition hinted that comet formation might follow similar rules across different planetary systems. Borisov was the first such object to be observed in detail. Apart from interstellar visitors, some comets have highly inclined or retrograde orbits that go against the general direction of planetary motion. These rare orbits suggest dramatic past events, such as gravitational nudges from giant planets or interactions with distant stars. Others exhibit orbital elements that change over time, hinting at hidden influences or dynamic instabilities in the outer solar system. Comets appear to emerge from unexpected directions, raising questions about gravitational interactions in the Oort cloud. It's possible that passing stars or even the galactic tide, the gravitational pull of the Milky Way, could be perturbing their orbits. These weak but cumulative forces may push icy bodies toward the inner solar system along paths that seem spontaneous or impossible. Long-period comets, such as C1-F1 or C2-2S1, follow orbits with periods exceeding tens of thousands of years. Their return paths are so elongated that they may never be seen again in a human lifetime. These orbits are difficult to predict precisely, because small forces or mass loss during solar flybys can cause significant deviations. The farther the origin, the less stable the orbit becomes. Occasionally, a comet's path brings it dangerously close to the Sun, a phenomenon known as a sungrazer. These objects often originate from fragmented larger comets and may disintegrate during their solar encounter. Some sun grazers, like Comet Lovejoy in 2011, survive their trip and re-emerge, albeit altered. Their orbits, which are extremely elliptical and tightly curved, reflect the complex gravitational interplay with the Sun's intense field. Another orbital anomaly occurs when comets are temporarily captured by planets. In rare cases, a comet may loop around a gas giant like Jupiter before being flung back into space. These interactions can drastically alter a comet's trajectory. Jupiter family comets, with orbits primarily influenced by Jupiter, are a result of such encounters and serve as a transition between long-period and short-period comets. Some researchers speculate that Planet 9, a hypothetical massive object far beyond Neptune, could be influencing cometary orbits. The clustering of certain long-period comets and trans-Neptunian objects suggests a gravitational source that has not yet been detected. If confirmed, this planet could explain several orbital outliers by reshaping the architecture of the outer solar system. Tracking comets with unusual orbits requires precise instruments and long-term observations. Because their trajectories are highly sensitive to initial conditions, even small uncertainties can result in large errors in predictions. Computational models must take into account non-gravitational effects, planetary resonances, and potential outgassing. These variables make the task of classifying an orbit a complex challenge. Comets with nearly impossible orbits are not just curiosities, they act as probes from the edge of our system, or even other stars. Each strange path offers new clues about the forces shaping our cosmic environment and what lies beyond the planetary orbits we know best, the local bubble our solar system floats in. The solar system is currently travelling through a region of space known as the local bubble, a vast low-density cavity in the interstellar medium. It spans about 300 light-years and has an irregular elliptical shape. The bubble is filled with hot ionized gas at temperatures reaching 1 million Kelvin. Despite its heat, it contains far fewer atoms than the surrounding regions of space. The local bubble likely formed from a series of supernova explosions that occurred 10 to 20 million years ago. These massive stellar events carved out cavities in the interstellar medium, pushing gas and dust away. The high temperatures and low density that remained created the environment we occupy today. As the Sun moves through the galaxy, it happens to be passing through this region. X-ray and ultraviolet measurements have helped identify the bubble's extent and composition. The hot gas emits faint X-rays, allowing researchers to map its boundaries. Measurements have also shown that the Sun is not at the centre of the bubble, but closer to its edge. Over time, the solar system may exit this region and enter a denser, colder part of the interstellar medium. The bubble is not empty. It contains small clouds of denser gas. The most notable of these is the local interstellar cloud, LIC, which the solar system is currently traversing. This cloud is much cooler than the surrounding bubble, but still tenuous compared to typical interstellar environments. It slightly affects the heliosphere, the bubble of solar wind that surrounds the solar system. The local bubble interacts with nearby bubbles, forming a network of cavities in the galactic plane. Some of these bubbles overlap or are separated by walls of denser gas. This structure is part of the larger local cavity, a complex network of interconnected voids and shells. Mapping this region helps astronomers understand the structure and history of the Milky Way's disk. Recent 3D maps, constructed from Gaia data and other stellar measurements, have revealed the detailed structure of the local bubble. Stars near its surface appear to have formed in a ring, suggesting that supernova shock waves compressed gas and triggered new star formation. This provides evidence that supernovae not only shaped the bubble, but also influenced its stellar surroundings. The existence of the local bubble also affects how cosmic rays and interstellar radiation reach us. With fewer particles and magnetic fields, this region offers less shielding from high-energy particles. This may have minor implications for planetary atmospheres and space weather. However, the solar system's magnetic environment, the heliosphere, provides substantial protection. The boundaries of the bubble create interstellar shock fronts, where hot, fast-moving gas meets cooler, denser material. These fronts can trigger complex chemical reactions and the formation of molecules. Observations of these interfaces provide insight into how different parts of the galaxy exchange energy and matter. The local bubble is a natural laboratory for studying these transitions. Because the bubble is expanding very slowly, it's considered relatively stable. but over astronomical timescales, the Sun will eventually move into a denser region. This could lead to changes in the heliosphere, increasing cosmic ray flux and altering the shape of our protective magnetic bubble. It's a reminder that space is not uniform. The solar system's environment is always changing. Some theories suggest that the initial supernova that formed the bubble may have had an effect on Earth. Although the explosions were too far away to cause extinction events, they might have increased cosmic ray flux or deposited isotopes like iron-60 in Earth's crust. These isotopic traces serve as geological evidence of nearby cosmic explosions in the distant past. Studying the local bubble also helps astronomers interpret data. Dust, gas, and magnetic fields affect the light we receive from distant stars. Understanding our local environment allows scientists to subtract its influence and see farther into space. Accurate models depend on understanding the space between stars as well as the stars themselves. The local bubble may appear empty, but it is a dynamic structure with a violent origin. It frames the current position of our solar system and reminds us that even quiet space carries the signatures of ancient cosmic events. Not all stars burn brightly or die dramatically. Many spend billions of years in quiet stability, slowly fusing hydrogen into helium in their cores. These long-lived stars are typically red dwarfs, small, cool, faint, and incredibly efficient. They burn fuel so slowly that their lifespans can exceed trillions of years, far longer than the current age of the universe. Red dwarfs make up nearly 75% of all stars in the Milky Way, but none of them have reached the end of their life yet. These stars shine at low luminosities, making them difficult to detect from Earth. Despite their quiet nature, they are among the most common and stable structures in the galaxy. Their longevity makes them prime candidates in the search for habitable exoplanets. Their small size means that fusion in their cores occurs at a slower rate than in larger stars like the Sun. They are also fully convective, meaning their material circulates from the core to the surface, evenly mixing the fuel. This allows them to burn nearly all of their hydrogen, unlike larger stars which leave much of their fuel unused. This efficient process is what gives red dwarfs their extended lifespans. Due to their faintness, many nearby red dwarfs were discovered only in recent decades. Proxima Centauri, the closest star to the Sun, is one such example. It hosts at least one exoplanet within its habitable zone, though stellar flares complicate the possibility of habitability. These flares emit bursts of radiation, but over long timescales, red dwarfs remain remarkably stable. Beyond red dwarfs, other quiet stars include orange dwarfs and certain white dwarfs in the later stages of cooling. Orange dwarfs, slightly larger and hotter than red dwarfs, also live for tens of billions of years. White dwarfs, on the other hand, are stellar remnants, cooling cores of stars like the Sun. Once formed, they radiate heat into space for billions of years. The lifespan of a star is primarily determined by its mass. Massive stars burn through their fuel rapidly and end in a supernova after just millions of years, whereas smaller stars do the opposite. They conserve fuel and remain quiet, contributing to a calm cosmic background. Their silence isn't due to a lack of activity, but rather a slow and steady nuclear process that produces light and heat over immense timescales. As these quiet stars age, they gradually increase in brightness and temperature. Eventually, they may exhaust their hydrogen and begin fusing helium, but this process occurs very slowly. For red dwarfs, this will take longer than the current age of the universe to even begin. Therefore, none have yet reached this stage, making their future behavior a subject of theoretical models. Some theories predict that after trillions of years, red dwarfs will become blue dwarfs, temporarily increasing in brightness. Then they will cool into black dwarfs, cold, dark remnants of stars that no longer emit light. However, the universe is too young for any black dwarfs to exist yet. These are predictions for a future far beyond anything observable today. The extreme longevity of these stars offers stable environments for planetary systems. A planet orbiting a red dwarf could remain in a relatively stable orbit for tens of billions of years. However, the same convective activity that fuels these stars may also generate strong magnetic fields and flares, which can affect planetary atmospheres and surface conditions. Due to their numerous and long-lived nature, red dwarfs are central to models of galactic evolution. They act as a long-term energy source and mass reservoir. Even when larger stars have gone supernova or become black holes, red dwarfs will continue to shine. In the far future, the universe will be populated mostly by these faint, silent stars. Astronomers study nearby red dwarfs to better understand stellar physics under low-mass conditions. These stars are used to test models of fusion, convection, and stellar atmospheres. They also help calibrate age estimates for planetary systems and contribute to our understanding of long-term stellar dynamics. Stars that live in silence are not inactive. They are the slow burners of the cosmos. Their quiet presence defines the long-term character of galaxies and the stability of countless potential planetary systems. The observable universe spans about 93 billion light-years in diameter, limited by how far light has travelled since the Big Bang. However, astronomers have detected cosmic structures so vast that they challenge this scale. These include massive quasar groups, galactic walls, and voids that span distances seemingly larger than theoretical cosmological limits. Their existence raises questions about the early formation of structure in the cosmos. One of the most puzzling examples is the huge LQG, Large Quasar Group, a structure composed of over 70 quasars stretching across 4 billion light-years. Quasars are active galactic nuclei powered by supermassive black holes. Their clustering over such vast distances was unexpected. According to the cosmological principle, matter should be evenly distributed on large enough scales. Structures like this seem to break that assumption. Another example is the Sloan Great Wall, a filament of galaxies about 1.4 billion light-years long. It is not a solid wall, but rather a dense thread of galaxy clusters. The existence of such a coherent formation was surprising, as models predicted a maximum scale for gravitationally bound structures. These discoveries force revisions in models of large-scale structure formation. Even more striking is the Hercules Corona Borealis Great Wall, which is estimated to span over 10 billion light-years. Its size is so extreme that some astronomers question whether it should even be classified as a single structure. If confirmed, it would be the largest known feature in the universe. Its presence raises the possibility of non-uniform early inflation or unusual patterns in cosmic evolution. Some researchers argue these may not be true objects, but statistical anomalies or linked chains of smaller structures. Others suggest these vast formations were seeded by quantum fluctuations in the earliest moments of the universe. Regardless of origin, their existence shows that cosmic architecture is more complex than once assumed. Cosmic structures larger than predicted raise concerns about cosmic isotropy, the idea that the universe is the same in all directions. If structure formation varies across space, it may point to early irregularities or hidden forces. Cosmic background radiation measured by missions like UMAP and Planck shows small fluctuations, but these massive structures exceed expected clustering patterns. Some theories explore the role of dark energy or modified gravity in allowing such formations to persist. Others propose that what we see as a single object may be an illusion created by line-of-sight alignments. Advanced simulations and redshift surveys help distinguish between true superstructures and observational artifacts. Large-scale structures are often organized into cosmic filaments, the skeleton of the universe. Galaxies form along these filaments, separated by vast voids of nearly empty space. This network is known as the cosmic web, and simulations suggest that its formation follows the growth of initial density fluctuations in the early universe. While most structures fit within the predicted limits of the cosmic web, the largest ones do not. These outliers provide a test for the standard model of cosmology, which relies on dark matter, dark energy, and general relativity. If these structures are real, the model may require adjustment or reinterpretation at the largest scales. Observations from surveys like SDSS and DESI are mapping the universe in greater detail than ever before. Each new survey increases the sample size of galaxy clusters and helps define the boundaries of the largest structures. More data will clarify whether these giant formations are exceptions or part of a broader pattern. Detecting cosmic structures near or beyond the visible limit involves measuring light that has travelled for billions of years. As we look farther, we also look into the past. These ancient signals carry the imprint of early cosmic conditions, and help reconstruct how the universe assembled its large-scale shape. Whether true giants or observational illusions, cosmic structures that approach or exceed the size of the visible universe continue to challenge our understanding. They are clues that may point to deeper physical laws or new stages in cosmic evolution. Polar ring galaxies challenge our understanding of mass distribution and angular momentum. Rings can form through resonance mechanisms, especially in barred spiral galaxies, when gas rotates at specific speeds relative to the bar's pattern. These rings often trace spiral arms and are well explained by orbital dynamics. However, they differ from the large detached rings seen in galaxies like Hogg's object. Some galaxies host multiple rings nested at different radii, possibly from successive star formation waves or feedback from central black holes. In some cases, dust lanes and warped gas clouds suggest past mergers. Observations in optical, infrared, and radio wavelengths reveal hidden components in ring galaxies. Cold gas, dark matter halos, and faint stellar streams shape ring dynamics. Sometimes what seems like a ring is part of a 3D structure viewed from a specific angle. Simulations show that ring-like features can form through internal feedback processes or satellite interactions. Reproducing objects like Hogg's object remains a challenge, indicating gaps in galactic formation theories. Galaxies with unexpected rings help refine our understanding of the galactic morphology and dynamics. They raise questions about dark matter, unseen satellites, and the long-term evolution of galaxies. Their rarity makes them valuable for simulations. Some ring galaxies have faint stellar halos, possibly remnants of past interactions, revealing clues about the galaxy's formation. Advances in telescope resolution continue to uncover more examples, adding to the catalogue of unusual cosmic structures. The Milky Way is surrounded by an invisible dark matter halo. Though unseen, its gravitational effects are clear. The rotation of stars and gas in the galaxy's outer regions reveals the presence of this unseen mass. Without it, the outer stars would move too slowly. Dark matter accounts for about 85% of the Milky Way's total mass. It doesn't emit, reflect, or absorb light, making it undetectable by conventional telescopes. However, its gravitational pull helps keep the galaxy's structure stable. Simulations of galaxy formation only match real data when dark matter halos are included. These halos extend far beyond the visible edge of the galaxy, reaching up to 300,000 light-years. Observations of stellar streams from disrupted satellite galaxies help map the halo's shape. The rotation curve of the Milky Way, which remains flat despite the increasing distance from the centre, is one of the first signs of dark matter's existence. Gravitational lensing is another method for detecting dark matter. When a background galaxy's light passes through the Milky Way's halo, it bends, confirming the presence of unseen mass. Dark matter is believed to consist of non-baryonic particles such as WIMPs or axions, though no direct detection has been made yet. The halo also influences galactic mergers and the motion of satellite galaxies. The interaction of dark matter from both galaxies during mergers shapes the structure of the galactic environment. Computer simulations like Illustris and Eagle show how dark matter halos drive cosmic evolution. Galaxies form inside these halos as gas cools and condenses. The dark halo, though invisible, plays a crucial role in guiding the structure and interactions of the visible universe. Some models predict dark sub-halos, smaller clumps of dark matter within the main halo, that could affect star clusters and gravitational lensing patterns. Detecting these would provide more insight into the small-scale structure of dark matter. Interstellar dust, made up of tiny particles scattered throughout the Milky Way, blocks light from distant stars and galaxies. This phenomenon, called interstellar extinction, can obscure the detection of alien civilizations. Dust clouds are most concentrated in the galactic plane, where stars are densely packed. Light from distant sources is dimmed and scattered as it passes through these clouds, making it difficult to observe objects in the affected regions. The presence of dust clouds complicates the search for technosignatures or signals from alien civilizations. A megastructure around a distant star could be hidden behind dense gas and dust. Even powerful radio or laser transmissions could be weakened or redirected by interstellar material, especially over large distances. Astronomers use infrared surveys to peer through dust clouds, as longer wavelengths penetrate the dust more effectively. However, even infrared light can be heavily scattered in dense regions, limiting the ability to detect planetary systems and artificial emissions. The zone of avoidance in the sky is a region heavily obscured by dust, making extragalactic observations in that area nearly impossible. If an advanced civilization exists within this region, it could remain undetected simply due to the dust barrier. Interstellar dust might also block or distort signals used for communication between civilizations, particularly high-frequency transmissions, which may suffer more attenuation depending on dust density. Low-frequency radio waves pass through dust more easily, but they are more vulnerable to cosmic noise and interference. Interstellar dust isn't evenly distributed. It forms molecular clouds, diffuse regions, and filaments that vary in size and density. Our solar system is located within a relatively clear region called the local bubble, a cavity in the interstellar medium created by ancient supernovae. This clear area gives us a better observational window compared to other regions. Dust not only obstructs visibility, but also makes exoplanet discovery more difficult. When searching for transits, the dimming of starlight by orbiting planets, any additional dimming from dust can skew results. This makes it harder to detect small Earth-like planets or accurately measure their atmospheres. Precision in exoplanet science relies on factoring in dust interference. Some astrobiology theories suggest that intelligent life could evolve in regions of the galaxy isolated by dust. Civilizations in these areas might develop without ever detecting signals from other stars due to their visual isolation. Dust, in this sense, creates cosmic silos separating potential civilizations. Research into mapping the 3D structure of interstellar dust is ongoing. Tools like Gaia and dust screening maps help astronomers identify which regions are more accessible for observation. This aids in prioritizing search areas for technosignatures and habitable planets. Future telescopes and surveys will use multi-wavelength strategies to better penetrate dusty areas. By combining optical, infrared, and radio data, scientists can more accurately map these obscured regions. As our detection capabilities improve, we may uncover signals that were previously hidden behind clouds of cosmic material. Interstellar dust is not just an obstacle, it's a fundamental part of galactic structure. It shapes what we can observe and, by extension, what we know about other possible civilizations. For now, it remains a quiet filter between our instruments and the deeper cosmos.